Hey everybody, Trey here. Welcome back to another video. It's been quite the active start to 2023 as far as severe weather goes across the U.S., and that was definitely the case in March and early April. We're in a little bit of a lull right now, but that was not the case, especially over the last couple of weeks where we had two very notable severe weather events from the Midwest down to the Mid-South. Very similar events as far as the forecast and the background pattern went, but very different outcomes. The first one was on the left, March 31st. We had two high-risk areas, a bimodal high-risk, one high-risk area there up in Iowa and Illinois, one down to the south across Arkansas, Mississippi, and Tennessee. This one was one of the more prolific tornado outbreaks we've seen in quite a while. Over 1,000 raw, unfiltered severe weather reports, almost 200 tornado reports, 131 tornadoes confirmed in total. This outbreak on March 31st actually is the fourth all-time tornado outbreak as far as tornadoes in a 24-hour period. That number coming in at 121, only behind the 2011 super outbreak, the 1974 super outbreak, and the 2020 Easter weekend outbreak. So a very prolific event, and this was you can see a very clear bimodal signal here as far as the tornado reports go, those red dots up there in the Midwest, and then a separate area down to the south, right where those high risks went. Just a few days after that March 31st event, we had a very similar outbreak on tap. Two areas of heightened severe weather potential on April 4th. Moderate risk area pretty much in the same spot as far as the northern mode goes from the March 31st event. And the southern mode a little bit shifted to the west, a little bit more north-south extent there from western Arkansas into southern Missouri. But the April 4th event was much tamer in comparison to the March 31st event. You can see here, still quite a potent severe weather event with almost 500 unfiltered reports, but just a few tornado reports sprinkled in there. Really not that strong bimodal signal, and not a very prolific outbreak as far as tornadoes were concerned. Just a few there up in Iowa and Illinois, and a couple there down in Arkansas into southeast Missouri. So even though these setups were quite similar as far as background pattern goes and the overall forecasts for these events where you had those bimodal risk area where the risk was at its greatest, we had very different outcomes to these events. So I thought, given that we're in a little bit of a severe weather lull here across the U.S., we'd go ahead and do a real deep dive into both of these events. We'll first take a look at the March 31st event, take a look at some of the factors that came together meteorologically to make this such a prolific outbreak, especially as far as tornadoes go. And then we'll compare and contrast that with the April 4th event, and take a look at the background pattern and why the April 4th event was relatively much tamer than the March 31st event. This is going to be probably a pretty long video. We essentially have four target areas or four different severe weather setups to go over. Two different heightened severe weather areas on 2 different days. So this one might be a long one. As always, I'm going to list chapters in the video description below, so you'll be able to skip around if you'd like. But this one might be a long one when it's all said and done. So without further ado, let's go ahead and get started. We're going to start off with the March 31st event. This was a very well forecast event. This is the initial day 2 convective outlook from the Storm Prediction Center. They have those two moderate risk, one in the Iowa, Illinois area, and one down to the south, centered around that Missouri Boot Heel vicinity. These two moderate risk areas were conjoined by the 13Z Day 1 outlook into one large moderate risk area, and then by the 1630Z outlook on March 31st. They put in those two separate high-risk areas. This was the first time that they had two separate high-risk areas in an outlook since the Day 2 outlook on April 13th, 2012, the day before the prolific tornado outbreak across the central and southern plains on April 14th, 2012. And this was the first high risk of any sort since March of 2021. So obviously a very high-end setup and one that warranted both of these high-risk areas. Again, over 1,000 severe weather reports for the entire outbreak, with 130 plus tornadoes confirmed so far in these two regimes. So definitely a setup that warranted those high risks, and the SPC did a great job in placing those high risks where the greatest threat for severe weather ended up being. All right, let's dive into the meteorology behind the March 31st event. We're going to start by focusing on the northern mode, and then we'll transition to looking at the southern mode of this event. We'll start out at 500 millibars, as we always do. This is at 12Z, 7 a.m. Central Daylight Time on March 31st. Right off the bat, you'll see we have a fairly high amplitude feature or trough moving into the central portion of the country. And you'll see if we were to draw a line through the axis of the trough that it is slightly positively tilted. You'll see it leans a little bit to the right there. That means that the trough is positively tilted. And we've talked about the difference between positively tilted and negatively tilted troughs before on the channel. It doesn't really matter the orientation of your trough. You are just as apt to get severe weather with a positively tilted trough as you are with a negatively tilted trough. However, the orientation and configuration and progression of that severe weather may be different when you have a nice, tightly wound, negatively tilted trough. And as you'll watch as we go through the animation here, this trough takes on a pretty textbook progression, textbook trough ejection into the Midwest down to the Mid-South. This is at 20Z, 3 p.m. Central Daylight Time. And if we draw a line through the axis now, you'll see it's definitely taken on more of a negatively tilted characteristic. So this is, again, a textbook evolution of the trough here, going from a high amplitude positively tilted feature, getting much more tightly wound, if you will, and then taking on a negative tilt. And as you can see here, this is our jet streak, strong winds rounding the base of that trough. And the reason why we had such a widespread area of severe convection or severe possibilities were that this exit region was very, very broad. You had the main core of the trough up in here, encroaching into the Iowa vicinity. But you also had this exit region where the winds spread apart here. That's all the way from the Midwest, Iowa, Illinois, down south to the Arkansas, Mississippi, Tennessee area. So a very wide exit region, if you will, of this trough. Going off of that, if we were to go up to 300 millibars, where we look for our defluence, or the spreading apart of those wind vectors in the upper levels of the atmosphere, you'll see that we have a very broad area of defluence aloft as that trough goes negative tilt. You see, not really that well defined initially, as that trough is is very neutrally to slightly positively tilted. Then once it takes on that negative tilt, you see a very stark increase in that defluence aloft, and I'll illustrate that for you here. Defluence aloft, again, is that spreading apart of the wind vectors in the upper levels of the atmosphere. That creates a void, and the atmosphere doesn't like that void. So what it tries to do to compensate for that is it brings air up from below to fill that void, and that's how we get large-scale rising motion or synoptic scale rising motion in a given severe weather setup. And so you'll see as we go to, this is at 20Z, 3 p.m. Central Daylight Time, you'll see the winds here over western Iowa are much more out of the south-southwest. Winds down here across, say, Arkansas into Mississippi and Tennessee, more out of the west-southwest. So a very broad region where the wind vectors aloft are spreading apart, and thus we had very strong defluence over this region, and there we had a large area of synoptic scale rising motion for ascent. Now you need, smaller scale boundaries and stuff to actually initiate storms, and we'll talk about that in a second. But overall, the synoptic scale or large scale rising motion for ascent was in place across the entire region, hence a very favorable corridor, a large corridor of severe weather potential with this particular setup. So once again, a very favorable trough ejection. We're back at 500 millibars here. Very favorable trough ejection for this event that was similar to some notable outbreaks in the past. And in our forecast discussion video for this March 31st event, I compared the trough ejection to April 27th, 2011. Not to say that this event was going to be, or now that we know what happened, was in any way close to the April 27th, 2011 event. That event is now the gold standard for tornado outbreaks in the United States. But the trough ejection was somewhat similar. So you'll see here at 500 millibars at 13Z on April 27, 2011, our trough centered up here in the Minnesota vicinity. And we draw our axis through the base of the trough, and you'll see definitely a positive tilt to the trough starting out in the morning on April 27, 2011. But as we go through into the heart of the event, you'll see it definitely takes on a much more negative tilt to it as we go into the afternoon hours on the 27th. We draw our axis now. Definitely a neutral to slightly negative tilt to that trough. Very favorable exit region and spreading apart of those wind vectors there in the exit region there over Mississippi and Alabama. And thus we had a very notable tornado outbreak. Very similar trough ejection with our March 31st event. Starts out as a positively tilted trough, winds up, gets very nicely negatively tilted as we go into the afternoon, and you'll see just a very favorable setup for, at least on the synoptic scale, for severe weather. We'll go down to 700 millibars now, take a look at any short waves moving little kinks in the height contours here that move within the main wave and provide somewhat more localized, enhanced areas of severe weather potential, greater lift, better severe weather ingredients in general ahead of these little shortwave troughs. So You'll see our main 700 millibar wave here, very broad, long wave trough. And you'll notice as we go into the afternoon, a shortwave definitely develops there. This is at 17Z noon Central Daylight Time. You'll see the little bit of enhancement there in the little kink there in the height contours. That is a shortwave trough. Right here at noon, centered in eastern Nebraska, central Kansas, moving quickly off to the northeast. And right ahead of that, you'll see as it swings through that Missouri, Iowa area. This is at 19Z, 2 p.m. Central Daylight Time, right ahead of that trough. Favorable area for lift and other severe weather ingredients, and that is why that area was favored for storm development going into the early afternoon hours on March 31st. Let's go down to 850 millibars. As you'd expect with a 500 millibar trough, a very notable 500 millibar trough with southwesterly flow traversing the Rockies, we would expect to see some low-level cyclone development east of the Rockies, and that's exactly what we got. By 12Z on March 31st, 7 a.m. Central Daylight Time, that 850 millibar cyclone was centered somewhere on the Nebraska-South Dakota border, moving off to the northeast slowly. Broad area of low-level jet in to the east and southeast of that trough. You see a broad swath there of 40, 50, even 60 plus knots of flow down here all the way from East Texas up into the Mississippi River Valley and up into the Midwest there. So broad low-level jet across the region. That 850 millibar cyclone would continue to shift off to the northeast very slowly through the day. You see it doesn't move a whole lot until that trough fully takes on a negative tilt and really ejects into that Midwest vicinity. By 20Z, broad low-level jet, somewhat weaker low-level jet closer to the core of that 850 millibar cyclone. That will come into play in a second here. But overall, from southeast Iowa into Illinois, Indiana, down to the south, Missouri, Arkansas, Mississippi, Tennessee, Kentucky, a broad swath of low-level jet, 40 to 50, 60 plus knots of flow down there. So a broad swath of low-level jet. That means, as we know, that low-level shear will be increased and that low-level warm, moist advection will be at a premium or at a maximum here, given that very strong low-level jet in place throughout much of the day. Similarly, going down to the surface, you'd expect to see surface cyclogenesis as that 500 millibar trough ejected over the Rockies somewhere in eastern Colorado, and that's exactly what happened. On the afternoon of March 30th, we started to see a surface low really tighten up there in eastern Colorado, and by 12Z, 7 a.m. on March 31st, it had translated across to generally the Nebraska-Iowa border vicinity and had deepened somewhat. 994 millibar low there, very strong surface low that would continue to meander to the northeast really until that surface or that upper level trough really took on a negative tilt and ejected. You'll see as that happens, coincident with that trough taking on a more negative tilt in the upper levels and really ejecting into the Midwest, that's when we see a continued deepening of that low. We go from a 994 millibar low to a 988 millibar low by 21Z, and you'll see the cold front associated with that pressure trough here. You'll see that cold front right in there, the pressure tongue associated with that kink in the isobars there really starts to swing off to the east pretty quickly. And that is when we see the surface low start to occlude, meaning that the cold front catches up to the warm front. If we were to draw that cold front from our center of the surface low there down through the pressure tongue, and we were to draw our warm front through our pressure tongue to the east of the surface low, you'll see they're very close together right in here. That means the occlusion process was starting, means that this surface low was very much at its peak maturity as that trough swung through. Became negatively tilted. That surface low really started to swing through off to the northeast and somewhat pinched off the warm sector with northern extent going into the late afternoon to early evening hours, but still plenty of warm sector to the south to work with for a broad area of severe threat with this system. So pretty classic surface low ejection here, surface low movement with the trough ejection, and this was a critical feature, this surface low here, deepening surface low in our severe weather threat for the northern mode. Let's take a look at our surface data for March 31st. This is at 12Z, 7 a.m. Central Daylight Time. First thing you see, our surface low located somewhere in here. You see that counterclockwise flow around that surface low. Cold front draped back to the west. A little bit difficult to tell exactly where it is, but you do see quite a temperature shift here across central Nebraska into central Kansas, and then areas off to the east, temperatures in the 60s there in eastern Kansas, eastern Nebraska, with temperatures trailing off into the 30s and 40s back here to the west. So the cold front is somewhere back in this vicinity right in here, roughly speaking. So the cold front well back here, you can see that moisture had been streaming northward. So see widespread mid to upper 50s dew points across the region with some 60s there across eastern Kansas into Missouri. That would continue to fill in as we went through the morning and afternoon hours, developing a broad warm sector across the region. We'll take a peek here forward a few hours. This is at 18Z. You can see that surface low had moved off to the northeast a little bit in here. Surface low somewhere right in that vicinity there. Hadn't moved too fast, as we said, until that trough really ejected, took on that negative tilt. That's when that surface low really deepened and started to eject off to the northeast as well pretty quickly. But for now, 18Z, just after midday, that surface low there in western Iowa, with 60s dew points now all the way up to Iowa, across Missouri, and then into Illinois, still upper 50s dew points. So a very broad warm sector, a very tight gradient here. Let me go forward 1 hour as well. You can really see it. Temperatures, or dew point temperatures in the 20s and 30s back here in eastern Kansas, transitioning to upper 50s to 60s there across Missouri. So a very tight gradient in here for our dry line, somewhere in this vicinity. Surface low up in here somewhere. So a very tight dry line there with ample moisture out ahead of it. At first glance, you might think upper 50s to low 60s, not the most favorable for severe weather, but when you have temperatures in the upper 60s to low 70s across the region, those temperature dew point spreads are going to be quite low and therefore still favorable for significant severe weather in this kind of environment. You can also see that the warm sector was very, very broad. We'll talk about this even more when we look at our southern mode. But you'll see those 60s dew points and upper 50s to 60s dew points stretch all the way from western Missouri into Illinois, eastern Illinois, and that warm sector would continue to shift off to the east with time as we went through the afternoon into evening on March 31st. So a very broad warm sector, lots of real estate for these storms to work with, and as a result, we were expecting several rounds of severe weather within this northern mode. We'll talk about those here in a second. So a very favorable look for severe weather. We will continue on through the evening, the late afternoon and evening. You see those 60s dew points entrenched into the region. That surface low finally ejecting off quickly to the northeast by late afternoon, as that the upper trough ejected, took on that negative tilt. Still very broad warm sector here. Illinois into southeast Iowa, dew points in the low 60s there. So definitely our surface pattern was very, very favorable for severe weather. Continuing on into the evening when we continue to have significant tornadoes, including one near Sullivan, Indiana, there in southwest Indiana. We'll talk about that particular storm as well. Still, you see those dew points even into the mid-50s there into Ohio. So, again, a very broad warm sector ahead of the dry line, giving these storms a lot of real estate to work with as far as a favorable parameter space went. All right, let's take a look at some observed soundings. We're just going to look at observed soundings right now. When we talk about some of the notable individual storms from the outbreak, we'll look at some wrap proximity soundings in close proximity to those individual storms, so you can see how the environment changed near those storms throughout the day and how the environment was different across the risk areas. So we'll start here with a few soundings, observed soundings. This is the 12Z Davenport sounding, definitely removed from the warm sector at this point. 48-degree dew point there at the surface, definitely away from the better moisture. As you can see, a little bit of an inversion there, and about a kilometer off the surface. Not much to speak of with this sounding here. Moisture through the column, fairly decent. Definitely some warm advection ongoing, though, at this location at 12Z, 7 a.m. on March 31st. You can see the veering of those low-level winds, that curvature in the low-level photograph. That does indicate strong low-level warm advection ongoing as that warm sector was beginning to take shape and get into place for our severe weather event later that day. Here is Lincoln, Illinois. Much of the same there, still removed from the warm sector, inversion there atop some weaker surface moisture, some cooler temperatures there, but still some very strong low-level warm advection ongoing at that location as well. We go a little bit farther to the west within the warm sector. This is at Omaha at 12Z, and you can see we are fully entrenched in the warm sector at this point, 64 over 58 there at the surface. Moist layer, decently deep moist layer there, extending up above 850 millibars, about 800 millibars or so. So a decently deep moist layer beneath that strong inversion there, indicative of the elevated mixed layer, the EML. Elevated mixed layer, or EML, we talk about it every video on this channel, it seems. That EML is that layer of warm, dry, well-mixed air that originates in the higher terrain areas of the desert southwest, western Mexico, even up into the higher terrain of the Rockies, And that, as a result, it gets transported off to the east or northeast atop that moist layer, and that can help cap the atmosphere and help allow instability to build in a given setup. So this is what we call a textbook loaded gun sounding. Deep, fairly deep moist layer beneath that elevated mixed layer, and that is a typical looking skew T diagram the morning of a significant severe weather event. That environment is basically getting ready to be used by these storms later on in the day, but that cap needs to be eroded first, and that was what would happen over the next several hours leading up to initiation. Long photographs here at this point at Omaha as well. Deep layer shear increasing with time, about 50 knots or so at Omaha at 12Z. We go down to Topeka, much of the same, still that loaded gun. That inversion not quite as prominent there, so definitely looking at perhaps fairly early initiation with this northern mode, as given the timing of the trough, the weakness, somewhat relative weakness there compared to areas farther north of this capping inversion would lead to perhaps early initiation in this regime. And that is not always a detrimental thing. You can have early initiation before peak heating, which occurs in the late afternoon hours. As long as your ingredients are there, storms can fire, they're going to be able to tap into those ingredients. So it doesn't matter that initiation might be a little early in this regime. If all the ingredients are in place, which they ended up being in place, you're going to get some significant severe weather, and that's what we got here. Still, elevated mixed layer was in place atop a decently deep moist layer up above 850 millibars there, 65 over 61 at the surface, and a hodograph that is pretty favorable for severe weather, deep layer shear over 50 knots, and that low-level hodograph very, very favorable for significant severe weather. And this is, again, at Topeka, was advecting off to the northeast, and so this is what was going to advect into our target area, particularly our high-risk area going into the afternoon on the 31st. Now, this is farther south at Norman, and this is a pretty ridiculous-looking sounding for 12Z on the morning of a severe weather event. Mixed layer Cape already above 2,500 joules per kilogram. Still, that elevated mixed layer in place. Moist layer very, very deep with southern extent. This was part of the reason that I chose the southern mode as well. As far as my chase plans for the 31st was that this moist layer was very, very deep beneath this somewhat decent elevated mixed layer. There was a very favorable look already, a highly unstable environment advecting into the warm sector at this point. Again, this was a little bit farther south. This was at Norman, our high risk, of course, in Iowa and Illinois, but this was going to advect in to the north and northeast across the warm sector as we went into the afternoon hours. Again, photographs favorable for severe weather already at 12Z. Now, I want to go back to the 12Z Topeka sounding here. So this is what happened between 12Z at Topeka and 16Z. You can see that that cap had fully eroded by 16Z in a matter of just a few hours. 16Z, 11 a.m. Central Daylight Time. That cap had fully eroded. So we had some forcing move in. The timing of that trough allowed that elevated mixed layer there to be lifted and cooled. And as a result, we had a deepening of that moist layer, fairly deep moisture there up to almost 700 millibars. That elevated mixed layer had been eroded completely by 16Z with a fairly unstable profile, over 1,200 joules per kilogram of mixed layer Cape. Wind profile's not quite as favorable. Here we were going, kind of moving to the south or southwest of our surface low in Iowa, so our wind profile is a little bit wonky here, but our thermodynamic profiles were indicative of what we'd see farther northeast as well. And these were certainly favorable given the better wind profiles up to the north and northeast near that surface low and out ahead in the warm sector. With this, coupled with this profile, thermodynamic profile, definitely a favorable look for severe weather. Now let's go to Davenport at 18Z. Still a little bit wonky, still that elevated mixed layer in place at 18Z, 1 p.m. Central Daylight Time. So areas out a little bit to the east, a little bit farther removed from the surface low and the forcing features, still had that cap hang on through about midday. This was at Lincoln, Illinois as well, same thing, but watch what happens here at Lincoln, Illinois between 18 and 21Z. So this is 18Z at Lincoln, Illinois. Still fairly prominent elevated mixed layer there, moist layer up to about 850 millibars or so, 70 over 58 at the surface. But watch here what happens by 21Z. Once again, that capping inversion had been lifted and cooled thanks to the forcing arriving. And now this is a pretty textbook look for significant severe weather. The cap fully eroded, deep moisture now above 700 millibars. This is an extremely deep moist layer here. The red profile, that temperature profile, and the green profile, very close together up to just above 700 millibars. So extremely deep moisture. And as that elevated mixed layer was eroded, we had very strong low-level warm moist advection to really deepen that moist layer and allow storm initiation there back into Missouri, up into Iowa, and those storms would move off to the northeast throughout the afternoon. This is, of course, a very favorable look for severe weather. Taking a look at the hodograph as well, this is another textbook look for significant severe weather. Strong low-level veering of those winds with height in those lowest levels of the atmosphere. Almost 400 meters squared per second squared of effective storm relative helicity. Deep layer shear, of course, favorable for supercells, now over 60 knots of effective bulk shear. Also, extremely strong low-level streamwise vorticity. We talked about streamwise and crosswise vorticity before. It's when you have your storm relative wind vector drawn from your bunker's right storm motion to your level of interest on the hodograph, and your horizontal vorticity vector, which is always perpendicular and to the left of your shear vector, which rides along the hodograph. So your horizontal vorticity vector there at the surface would look something like this. When these two vectors are parallel, that's when you have streamwise vorticity. And streamwise vorticity, I use the analogy all the time that think of it as an NFL quarterback throwing a football with that perfect spiral. The air is spinning in the atmosphere, and as these maturing supercells ingest this spinning air, when you have streamwise vorticity, that spin is already oriented in the right direction. So the storm doesn't need to do much to get that stretched and tilted into the vertical and undergo tornadogenesis later on in its life cycle. So streamwise vorticity is a lot more favorable for tornadogenesis in supercells than crosswise vorticity, which would be when these vectors are more perpendicular to each other. And you can see that streamwiseness was the case through quite a bit of that lowest layer of the atmosphere here. If you draw our vector to our hodograph up here, for example, you'd see that those vectors are definitely fairly parallel to each other, going up there a kilometer or two in the atmosphere. So a very favorable look for significant severe weather in that hodograph. Again, this is at 21Z, 4 p.m. Central Daylight Time at Lincoln, Illinois. We can also decipher some supercell characteristics from this hodograph. First, we'll start off with our storm relative inflow in the low levels. When that is stronger, that is indicative of supercells that are a little bit larger in size. When you have much weaker storm relative inflow, i.e. this vector from the storm motion vector to your hodograph in the low levels, when that's shorter, you have much smaller supercells. You can see here that our storm relative inflow, 10, 20, 30, 40, 35 to 40 knots or so, definitely indicative of a little bit larger supercells. Now, our storm relative outflow, generally above 6 kilometers or so. When that vector is longer, that means you have precipitation that's vented out away from the mesocyclone region of the supercell, and you can have a much easier time viewing any tornadoes with these supercells. You have 10, 20, 30 plus knots or so above 6 kilometers. That's that yellow and light blue portion of the hodograph. So generally, that's kind of right in the margins for your classic supercell structures. That 30 to 35 knot range or so is indicative of classic supercells. Anything less than that tends to be a little bit more high precipitation. Anything much stronger than that tends to be more low precipitation. And in this case, we're right in that classic range for supercells. So from a meteorological perspective, this had pretty much everything you'd want to see for a significant tornado outbreak. Strong negatively tilted trough moving in, strong defluence aloft there in the exit region. Strong notable shortwave moving in at 700 millibars to initiate those thunderstorms in the warm sector. Broad, strong, low-level jet across the region associated with that strong low-level cyclone, 40, 50 plus knots over a very broad area, and a strong surface low and extremely broad warm sector for lots of real estate for these storms to act upon and have a longer duration, significant severe threat. So everything was pretty much there for a significant severe weather outbreak in this northern mode. And there were really two different targets you could choose. You had the storms along the surface low up there closer to the surface low in Iowa. That was very similar to a cold core type setup. We've talked about cold core type setups before. I'll put the link to my guide to cold core tornado environments video in the link in the description box below. But we looked at this diagram from Davies and Geyer 2004 that shows the processes at play and the orientation of the surface of the features at play for a cold core tornado setup. And you had a lot of those going for you in the northern mode near the surface low. Surface low there, close proximity to the 500 millibar low aloft. You see the surface low there. This is at 18Z. They're in west central Iowa. We go to 500 millibars. The core of that trough moving in from the west. So fairly close proximity between the core of the 500 millibar cyclone and the surface low. So we checked that box as well. Very cold air aloft associated with this, helping to destabilize the atmosphere very rapidly along that surface low. As we went into the afternoon hours, a little bit less low-level shear. We'll take a look at some proximity soundings from the Keota, Iowa tornadic supercell there, closer to the surface low that didn't quite have as much low-level shear as areas farther to the east, but still a very favorable environment, very cold core-esque environment for tornadic supercells, using a lot of the processes we learned about in Davies and Geyer 2004. Another hallmark of these cold core type setups is the low-level instability, usually very strong in these cold core-esque setups because of strong surface heating and that very cold air aloft moving in that really helps destabilize the atmosphere and can really help stretch any spin near the surface into the vertical to aid in tornadogenesis in supercells. And this is the plot of 0 to 3 kilometer mixed layer CAPE and surface vorticity on March 31st. This is at 17Z, 18Z, 19Z, 20Z right there, and we've done a video on this before, the tornado forecasting cheat code. It's this 0 to 3 kilometer CAPE and surface vorticity, bullseye right there in southeast Iowa. And if you don't know where exactly the most notable tornado of that northern mode occurred, near Keota, Iowa, well, it's right in that bullseye. So a very favorable look in the low-level thermodynamic fields for a tornado threat, given somewhat stronger low-level shear than a typical cold core event, even though farther to the west, closer to the surface low, it might have been a little bit decreased, a little bit out of the main low-level jet axis. Still plenty of surface vorticity along those surface boundaries, and enough low-level shear that this very strong 0 to 3 kilometer CAPE was able to stretch that very efficiently into the vertical and aid in tornadogenesis in those supercells. You also had the target along the dry line. So the dry line off to the south, dry line, cold front sagging back here, dry line somewhere in eastern Kansas, and you had storms firing on that. Fairly north-south oriented dry line, shear vectors very much perpendicular to that dry line. You'll see there the effective bulk shear vectors. Actually, we'll use the 0 to 6 kilometer shear vectors, a little bit better proxy there. So your north-south oriented dry line, shear vectors definitely a good amount perpendicular to that dry line. This is pretty much a textbook angle for those shear vectors, between the shear vectors and the initiating boundary, which is in this case the dry line. So you're going to have discrete storms, and that's exactly what happened in the northern mode. Here's our visible satellite imagery from March 31st. You see we wake up with a little bit of activity here across Illinois and Indiana, but that quickly moved off to the east. A little bit of cloud cover remaining in the warm sector across southeast Iowa into Illinois, with some thunderstorm development back there in Missouri initially. This would somewhat help temper the overall vertical mixing, although we do have quite a bit of sunshine across the region. We'll talk about vertical mixing a lot more when we get to the April 4th event. But vertical mixing, as we've talked about before, is when you have intense surface heating, and as we know, warm air rises. Well, when that warm air rises off the surface, when it's being intensely heated by the sun, that warm air rises, but it can also bring down drier air from aloft to the surface, and you can see surface moisture crater a little bit in the early afternoon hours when you have that strong surface heating ongoing. And that was a big player in the April 4th event. We're going to talk about that more again in a little bit when we look at the April 4th event. This one, not so much. We did have number one, strong low-level warm moist advection, that surface low, strong southerly winds in the warm sector, helping to pump and sustain that moisture in the that moisture surge and advection in the warm sector. You also had some muted cloud cover here across the region from these early storms, and the early cloud cover there across Iowa and Illinois to help at least temper the mixing a little bit in these regions. So mixing was not really a factor. We did see dew points maybe drop a couple of degrees, but still not a very drastic change given strong low-level warm moist advection to help offset the mixing. So not a big deal here, even though we did see quite a bit of sunshine in the warm sector, and by late morning, early afternoon, we started to see storms fire there across Missouri. And then our first round of significant severe weather was evident here by about midday across the region. And you can see this is about as textbook a look for a tornado outbreak as you'll ever see. Discrete supercells along the dry line here, very discrete updrafts up all the way down the dry line there, moving off of the dry line, away from each other, at least initially. And in this kind of environment that was taking shape, strong low level and deep layer shear, strong low level thermodynamics in that strong low level instability that we showed, this was going to be a pretty significant tornado outbreak, and we had several tornadic supercells develop, most notably this one here in southern Iowa that would produce the twin tornadoes near Keota, and one of those was rated an EF4. And then eventually things got a little bit more messy as the forcing became stronger. That trough up in the upper levels rotated in. We started to see storms form more, congeal into more of a messy storm mode, and eventually we transitioned to more of a damaging wind and embedded tornado threat in those lines. Let's take a look at the radar now. So you'll see some of those early storms. This is at 7 a.m. Central Daylight Time here. Early storms across Illinois and Indiana moved off very, very quickly. There was some concern that those early storms would be an issue with destabilization in this setup in the northern mode, but that was not the case. We had a couple of those thunderstorms develop there in Missouri early on. Those didn't do a whole lot, but then you see there that initial round along the dry line there in far eastern Kansas, western Missouri, just an absolutely textbook view. That's why they upgraded to a high risk, was the development of these discrete storms along the dry line, moving into an extremely favorable environment for tornadic supercells. And you see here they marched along fairly discrete for quite a while, especially this one, these few here in northeast Missouri to southern Iowa. This was the Keota tornadic supercell. These ones were in a similar environment, although they did not produce tornadoes. I've had some questions about why the storm in particular near Hannibal, Missouri, this one here, discrete all by itself, did not produce tornadoes. And it looks to me like there was some pretty destructive interference from those storms to the south. If you see this cluster down here, this is not going to be a favorable look for a continued tornado threat with that Hannibal, Missouri storm moving into western Illinois. This is not your situation where you have an ongoing supercell and maybe you have just a little shower that's feeding up into the forward flank that could enhance tornadogenesis through that storm merger. This is a whole complex of storms catching up with this storm right here, hampering the tornado threat and really nixing any threat for a significant long track tornado as it quickly became absorbed by the line, and the storm mode became a lot messier there. Whereas with the northern storms, you had they were able to sustain for quite a while, specifically that Keota, Iowa storm, for quite a while out ahead of the stuff back to the west, forming near the surface low, and so that was able to produce pretty significant tornadoes there. And then eventually it did catch up with the line and become somewhat of a bookend vortex there, and the significant tornado threat decreased just a little bit. Continuing on into the nighttime hours here, we continue to see these somewhat of a messy storm mode, but we did have a few discrete storms be able to sustain themselves out ahead of the main line, particularly this one to the south. This one would cross into Indiana and produce a significant tornado near the town, or in the town of Sullivan, produce some very significant damage there with that sustained discrete storm out ahead of the main line behind it. Discrete storms in this environment were going to produce significant tornadoes, no question. That's why they upgraded to the high risk. And eventually things did congeal into more of a line and weaken as they moved into Indiana and Ohio. All right, let's talk about a couple of the notable storms from this northern mode. The first one we'll talk about is that Keota, Iowa tornadic supercell. Some incredible images and footage have come out from this supercell. Had two tornadoes in progress at once. Just a super impressive shot here, and we've seen a lot of shots like this with these two tornadoes ongoing. The stronger one here was rated EF4. This footage here shows you how strong this tornado was. Just absolutely beautiful footage here, tripoded footage of this tornado, and it turns into a monster. Does quite a bit of damage here. This zoomed in shot shows you just how strong this tornado was. Just visually, you can tell with all the debris in the air, the strong rotation within that vortex. This was a strong tornado. Again, was rated EF4. Very impressive footage here. So, once again, want to thank Peter Corman for allowing me to use these storm-centered radar loops. This is the storm-centered radar loop from the Keota supercell. You'll see it forms here northwest of the Kansas City area, all the way back in northeast Kansas there, right about midday or so. Moves off quickly, goes through some stages where, we've talked about this before, where sometimes in these strongly sheared environments, discrete storms, singular updrafts have a hard time surviving, but when you have a little bit of clustering, when you have multiple updrafts together kind of clustering, they can help withstand that shear before and allow one to become dominant. And that's exactly what happened here. You can see multiple updrafts congealing there over time, and then it eventually turns into one supercell here. This is at just after 18:30 Z, so about 1:30 p.m. or so as it moves into Missouri. Definitely a dominant supercell here. Large hail occurring. No tornado threat yet. Once again, low-level shear remained a little bit weak initially before that low-level thermodynamics really improved, and that low-level shear improved as well as that trough took on that negative tilt. Moves off into northern Missouri. Still not doing a whole lot. Some large hail. Some evidence of low-level mesocyclone here as it crosses the border into Iowa. This is Iowa. This is Missouri. And so it does have some semblance of low-level rotation as it moves into Iowa, and then eventually it starts to really ramp up as it moves toward the Unionville, Iowa area, and then eventually it moves toward Ottumwa, at which point it really starts to ramp up. Tornado in progress here. Very strong tornado, just still a very discrete supercell. Went through that coalescence process, if you will, and maintained its discrete nature well out ahead of the line to the west. Strong rotation there, and you can see multiple times where it has potentially two different couplets right here, south of Hedrick, northeast of Ottumwa. Strong couplet there, potentially another strong couplet right in there as well. So, and then as it moves off toward Keota, up in here, two distinct couplets. We switch the radar view here. But you can see two distinct couplets as it moves off toward Keota. One in here, it looks like, and one in there as well as it moves into Keota, producing some significant damage, as you saw there. Once again, northeast of Keota, one there, one there. So that just shows you lots of streamwise vorticity in the environment being ingested by this supercell. And if we look at the image here, you can even see in this mesocyclone here, you see almost this pancake stack type feature here. That is indicative of maybe a little bit of convective inhibition perhaps remaining, but it more so indicates the incredible amount of streamwise vorticity in the environment. Once again, that's the NFL player throwing that football with the perfect spiral. That supercell is ingesting that streamwise vorticity, and it's very easy to turn that into a tornado, as we saw with this supercell, especially with strong thermodynamics. So all in all, a very favorable look with this storm. Lots of streamwise vorticity in the environment. Let's take a look at some soundings. These are rapid proximity soundings. We're going to look at two sets of proximity soundings. This is from Ottumwa, Iowa. We saw that the supercell passed literally right over Ottumwa. We're also going to look at Burlington, Iowa, which is just a little bit off to the east. And this will show you how the environment was somewhat bifurcated. A little bit farther to the west, weaker low-level shear, but stronger low-level thermodynamics. Farther to the east, a little bit stronger low-level shear to deal with. We'll first start with Ottumwa. And so this is Ottumwa, and we'll show the map on the screen here. Keota is just to the northeast of Ottumwa. So we start off at 12Z, once again, very deep moist layer. Beneath that elevated mixed layer there, a little bit of drier, well-mixed air aloft. And that would remain the case throughout much of the day until that trough started to move in. This is at 17Z. And again, this is a couple hours before the tornado moved into southern Iowa. Very strong low-level instability at this point, 0 to 3 kilometer cape. Over 120 joules per kilogram. You can see there, much fatter cape there in the low levels. Deep layer instability as well, over 2,200 joules per kilogram of mixed layer cape. So that cap had eroded thanks to the arrival of that shortwave, strong surface heating, strong moisture advection, and that was going to continue through the afternoon. Now you'll see that the low-level shear profiles here, this is at 19Z. Take a look at our hodograph. Thermodynamics remain very favorable. Our hodograph, though, at first glance, you wouldn't expect this to be a significant tornadic supercell type hodograph. Low-level shear, very, very weak. We still have a little bit of veering in those low-level winds, a little bit of curvature there in the low-level hodograph. but effective storm relative velocity only just over 100 meters squared per second squared. We don't see a ton of curvature there in the low levels. So this is a little bit farther to the west. And again, we were a little bit farther removed from the low-level jet axis. Therefore, our low-level shear was not all that strong. And this also, just as a side note here, surface winds out of the south-southeast there are almost 20 knots. So that shows you that we don't always have to have strong surface wind for significant tornadoes. In fact, if we were to have a surface wind maybe of 10 knots out of that same direction, you can see how the curvature in the hodograph would change. We'd have a lot more curvature to deal with, a lot more low-level shear to deal with, and therefore a larger low-level hodograph, more favorable for significant tornadoes. So that just, you hear this all the time, that no flow, no show, no surface flow, no show, meaning that if you have calm surface winds, you're not going to see tornadoes. That's just not true. It depends on the orientation and the configuration of the wind profile. Sometimes if you have a little bit weaker storm relative low-level winds, you can actually have stronger low-level shear and perhaps stronger potential for tornadoes. But that is an aside. We'll get back on topic here. The point is, we had very strong low-level thermodynamics, but not super strong low-level shear. So that, of course, is compensated by these low-level thermodynamics. When you have very strong thermodynamics, strong instability in the low levels, it's going to take any low-level shear, any spin in the low levels, whether that's vorticity along surface boundaries, as we know we're fairly close to the dry line here, just south of that surface low, so some surface vorticity in play. If we were to look at our surface vorticity map here, you see we do have these blue lines, these blue contours are our surface vorticity. Some overlap with that stronger 3-cape bullseye there, but overall not a strong amount of low-level shear. It doesn't really matter in these kind of environments when you have strong stretching of any spin or low-level shear near the surface. That's going to be stretched very efficiently into the vertical by this very strong low-level instability, and that's exactly what happened with this supercell. We move on a little bit more. You see that we do have that instability maintain itself, very strong instability, strong low-level instabilities, 0 to 3 kilometer cape above 100, with modest low-level shear. Now, if we look at Burlington, which is just off to the east a little bit, we'll show you that we were kind of right in the middle of these two environments with this Keota supercell. So you'll see very similar starting the day, deep moist layer, beneath that inversion, strong wind profile, strong warm advection in play. And as we go into the afternoon, you'll see that the low-level shear decreases, but eventually we see a stark increase in that low-level shear. Thermodynamics very similar, strong deep layer instability, low-level instability also more than adequate for supercells, tornadic supercells, but this low-level shear profile, very, very favorable, a lot more favorable at first glance than areas out to the west. This strong curvature there in the low-level hodograph, strong veering of those winds with height in the lowest levels. This is a much more favorable, significant tornado hodograph at a surface glance than the one at Ottumwa. So I think we were right in the middle of these two events. We were just barely on the western edge of the stronger low-level jet in that Keota, with that Keota supercell, but still in that very favorable low-level thermodynamic environment. Very reminiscent of the Winterset, Iowa case from March 5th of last year, where you had a very cold core-esque setup, strong low-level instability, but you also had strong low-level shear, which helped, I think, aid in the significant tornado potential on that day. Very similar to this day as well. Strong low-level shear with strong low-level instability is always a combo that's going to raise some eyebrows. All right, let's talk about the Sullivan, Indiana tornadic supercell. Haven't seen any pictures of the actual tornado, but this is some damage footage via drone from my friend Aaron Rigsby, and you can see some very intense damage with this tornado. This was rated EF3 and was a long tracker, so very intense tornado here. Let's take a look at the radar. This formed well to the southwest back in southeast Missouri, well south of St. Louis. Took some time to get going. We see some clustering of those updrafts, and eventually a discrete supercell takes over. Starts to develop some low-level rotation as it crosses into Illinois right there, but still needed some time to get going. As it approached the Indiana-Illinois border, it finally got going, saw a strong shear signature there. Very strong shear signature, inbounds and outbounds both increasing, and then we would see low-level rotation tighten very quickly, and we got a significant tornado as it passed into Indiana right there. Here is the town of Sullivan,
And again, this was a very strong tornado, discrete supercell. In this kind of environment, you see the classic hook there with perhaps a debris ball there. Definitely some debris, a large debris signature on correlation coefficient there. So a significant tornado, no question, passed through Sullivan, causing some significant damage. Moved off into Indiana before getting sucked into the line, or absorbed into the line, and terminating its tornado genesis there well into Indiana. All right, we're going to look at some soundings from Terre Haute, Indiana, which is about 25 miles to the north of Sullivan. You see it on the map there. Here is the 12Z sounding. Instability out farther to the east was not nearly as favorable as it was over Iowa and Illinois. And you'll see that here in these soundings. This is the 12Z Terre Haute sounding. Only 54 over 51 at the surface. Very stout inversion, well removed from the main warm sector. And that would sustain throughout the day. We didn't see a whole lot of instability build up throughout the day. By 1Z, you'll see that instability was fairly minimal, just over 400 joules per kilogram of mixed layer CAPE. Very skinny looking low-level instability profiles there. But as we've talked about many times before, especially in cases like the Greensburg, Kansas case from 2007, if you have a mature discrete supercell going on in an environment and the instability in the low levels starts to get sapped, or some capping gets builds back in, that supercell can sustain for quite a while if there's strong deep layer and low-level shear. And my goodness, did we have that in spades out here to the west. Take a look at this photograph as we go through the day. By 1Z, look at this photograph. This is unbelievable. Deep layer shear, extremely strong. 85 knots of effective bulk shear. And look at that low-level photograph. Extremely strong veering and strengthening of those winds in the low levels, from basically 20 knots there at the surface out of the southeast to 70 plus knots there at about a kilometer off the surface out of the south-southwest. So strong veering, very much impressive strengthening of those winds in the lowest levels. And that leads to this kind of a hodograph. Just incredible curvature there in the hodograph. Effective storm relative velocity over 700 meters squared per second squared. So no wonder we had a significant tornado. Despite the lack of instability there in southwest Indiana, this shear profile was going to be able to make up for the shortcomings in the instability department, and it definitely did with that long track discrete supercell out ahead of the line from southeast Illinois into southwest Indiana. Very strong streamwise vorticity as well in this profile. We draw our storm relative wind vector and our horizontal vorticity vector, which is perpendicular and to the left of the hodograph. Those are very parallel to each other, and that is the case throughout the lowest kilometer or two of this hodograph, indicating extremely strong streamwise vorticity, a very rich, streamwise vorticity rich environment for the supercell to work off of. So amid very large low-level shear in general, strong streamwise vorticity was able to be tilted and stretched into the vertical with this supercell to aid in tornado genesis. All right, let's transition to the southern mode on March 31st. We'll go back to our 500 millibar map, and right away you'll see the difference between the placement of these two high-risk areas with respect to the jet streak within the trough. So right here, you'll see the jet streak rounding that stronger flow rounding the base of that trough. In the southern mode, we were just on the southern fringes of that jet streak, whereas in the northern mode, clearly in that left exit region of the trough, taking the brunt of the main forcing associated with the trough. But here in the southern mode, we were just on the southern flank of that forcing, and that right away should pique your interest and make you think that that could be a little bit more favorable for discrete supercells given a little bit weaker forcing down in that southern mode. We'll go back to our April 27th, 2011 event, and you'll see a very similar thing happen. Here's our main jet streak associated with the trough. And where did all those tornadoes happen on April 27th? The bulk of them happen here just on the southern fringes of that jet streak. So the forcing was a little bit weaker. We had some features there in the warm sector, some subtle forcing features in the warm sector, prefrontal confluence bands, etc., that helped to initiate more discrete storms given a little bit weaker forcing. Same thing here. My interest always gets piqued in the setups where you're just on the southern flank of the jet streak, as the forcing is a little bit weaker there in that region compared to right in the left exit region of the trough. Now, one thing I want to mention here is if we were to break this jet streak up into quadrants, and this may get a little bit scientific, we'll try to keep it a more basic demonstration here. But if we were to break this jet streak up into quadrants here along the axis of that trough, the left exit region is going to be your favored area for your most favorite area for severe weather is in this region. Divergence aloft is favored. The spreading apart of those winds aloft is favored, and that yields convergence at the surface. And convergence is usually associated with the surface low. So that's usually why you'll hear people say the left exit region is your most favored, more premium sector of the trough for severe weather. Now, if you were to look at this quadrant model, the southern mode was clearly in the right exit region of this trough. Generally in the right exit region of a trough, of a jet streak, convergence aloft is favored, which yields divergence at the surface. And of course, as we know, that can be somewhat unfavorable for severe weather. But this is very subtle, and not all troughs are going to be really sticking to those theorems. And this was the case here. You still had fairly strong defluence aloft. If we were to go to 300 millibars here, and I'm going to go forward a little bit in time, you'll see we still have decent defluence aloft here over the southern mode. You'll see here clearly in the northern mode, we already took a look at that, very strong defluence aloft there, creating that large-scale rising motion for ascent. Still have a little bit of defluence down here as well. These wind barbs in northern Arkansas out of the southwest, very slight curvature there, more of a west-southwest flow there in southern Arkansas into Louisiana, as you go farther toward the southern extent of this trough. So a little bit of defluence aloft over this region. Even though it's the right exit region, you'll hear people say, "Oh, the right exit region is no good for severe weather." That's not always the case. We've seen a lot of severe weather outbreaks occur in the right exit region, especially with a negatively tilted, very textbook-looking trough like this. So there was going to be severe weather in this southern mode. Just perhaps the threat for discrete storms, long-lived discrete supercells with significant severe hazards, was maybe a little bit more likely down here in the southern mode, given a little bit weaker forcing. Now we'll go down to 700 millibars. The effect of the shortwave trough that we saw in our northern mode, perhaps not quite as prominent here in the southern mode. You'll see here it's at 18Z, 1 p.m. Clear kink in those height contours there up to the north. Not so much here down to the south. Fairly flat flow there within that southern mode. But what was the key in this southern mode, along with a very strong low-level jet, perhaps a little bit stronger even than areas farther to the north? You'll see at 850 millibars here, 50 to 60 knots with this southern mode, 35 to 40 knots or so with the northern mode. Still strong in the north, but a little bit stronger there in the south, so low-level shear may have been a little bit stronger, at least initially, in this southern mode. But the key here was a very notable prefrontal trough that took shape over the warm sector. So you'll see here on our surface map, we'll go to about 16Z, 11 a.m. Central Daylight Time. Here's our surface low. Main surface low is up in there. Cold front trailing back to the southwest through that pressure tongue. And if you look off just to the east of there, you'll see a little bit of a kink in these pressure contours here out ahead of the cold front in the open warm sector. That is a clear prefrontal trough, and we talked about this in our forecast discussion. And in many of our forecast discussions in prior events, that these prefrontal troughs are classic initiating mechanisms for more discrete supercells. Because the forcing is so weak along them, prefrontal confluence is fairly weak, so you only get a few updrafts along them. In general, you'll see here as we go on with time, that prefrontal trough maintains itself. This is 18Z, clear little kink there, leading into central Arkansas. Just out ahead of that prefrontal trough is where those storms were most prominent there across central Arkansas, which we'll talk about here in just a second. So very notable prefrontal trough, very weak forcing mechanism, along with the somewhat weaker synoptic scale forcing mechanism. This is a classic recipe for discrete storms, and that's exactly what we got. Let's go to our surface data here. We'll start at 12Z. And you'll see right off the bat as well, very broad warm sector, 60s dew points all the way into western Oklahoma, west central Texas, stretching all the way into Mississippi. So an extremely broad warm sector, even broader, more broad than farther north. So lots of real estate for storms to work with here. And these broader warm sectors are always much more dangerous in these high thermodynamic, high kinematic events. When you have a large area where storms can have favorable ingredients, you are going to see a long duration severe threat and a greater threat for long track significant severe weather. And that's exactly what we got here. Very broad warm sector with southern extent, that cold front lagging behind. Again, the main forcing with the trough farther to the north, so that cold front down to the south lagging a little bit farther behind. And therefore, that warm sector remained very broad as we went into the afternoon hours here across the region. Winds started to veer, though, to the west near that cold front, but we still had very nice backed winds for the most part across the warm sector, across Arkansas into Louisiana, Mississippi, and Tennessee. Winds out of the south or south-southwest here, not too much given a strong southwesterly low-level jet. Still going to have very strong veering of those winds in the lowest level, strong low-level shear. Dew points here, very high, a little bit higher than farther to the north. Dew points in the mid-60s. Little Rock there at 17Z. Midday, 77 over 65. 79 over 68 down here to the south. So very juicy air mass across the region. You can also clearly see the confluence band associated with that prefrontal trough here. This is at 17Z. Noon on March 31st. You can see the winds here across eastern Oklahoma into North Texas, far northwest Arkansas, more out of the southwest, where we have a little bit more backed flow here in west central Arkansas, Russellville there out of the south-southwest. So clearly a confluence band here across western Arkansas that was allowing storms to fire up along them. Again, fairly discrete storms, given that weak forcing weak confluence along this prefrontal trough. As we went toward 2021Z, still a very broad warm sector, very juicy air, 79 over 66 there in northwest Mississippi, 74 over 63 there at Memphis, 79 over 66 there at Stuttgart, Arkansas. So extremely favorable low-level moisture profiles there across the warm sector for significant severe weather, and that would last throughout the evening as well. You see those 60s dew points seeping into Alabama there. So this was going to continue the severe threat. As long as we had discrete supercells, that severe threat was going to continue well into the evening hours, and that's what we got. Several strongly tornadic supercells after dark in this regime, before winds eventually did start to veer significantly as the cold front approached there. You'll see those winds very much out of the southwest as we went into the evening hours. So eventually things did congeal into more of a messy storm mode, but we had a much longer duration threat for discrete supercells in this southern mode. That's why I chose to chase the southern mode, as I thought the threat for significant long-track tornadic supercells was greater here to the south and farther to the north, where the forcing was a little bit stronger. Still very favorable thermodynamics and kinematics up there, but I was a little bit unsure about the storm mode. It ended up not being an issue, as we saw in that northern mode analysis, but I thought the threat for long-track discrete supercells here was going to be a little bit greater in the southern mode. All right, let's take a look at some soundings. Just like our analysis of the northern mode, we'll take a look at some observed soundings first, and then when we investigate some of the individual storms in the southern mode, we'll look at some wrap proximity soundings for a little bit closer look at the environment. So this, as we already saw, is the 12Z Norman, Oklahoma sounding, very deep moist layer with elevated mixed layer above it, strong instability building, deep layer and low-level shear profile favorable for severe weather. That was much of the same at Fort Worth, a little bit stronger capping inversion down to the south there, a little bit shallower moist layer, but still a very favorable looking loaded gun sort of profile for a severe weather event. Here is 12Z at Little Rock, much of the same, deep moisture extending up above 850 millibars with that elevated mixed layer in place. So that was going to mostly hold off convection in the warm sector out ahead of that prefrontal trough through much of the morning. We did see a few showers and maybe a couple rumbles of thunder in there across central Arkansas, but skies quickly cleared. We'll show the visible satellite in just a second. The overall look to the sky became pretty favorable out ahead of those developing storms to the west along the prefrontal trough. Here is Jackson, Mississippi as well, much of the same there, inversion in place with somewhat shallow moisture. Interesting low-level profile there, a little bit wonky there at Jackson. So Little Rock, I think, much more representative of the overall region. This is Shreveport, same thing as well. Now let's go from 12Z Little Rock to 18Z. So here's 12Z at Little Rock. Here is 18Z. You see what happens between 12Z and 18C. Pretty much fully destabilized, just some very tiny remnants of that elevated mixed layer left. But look what happened to the moist layer. Here again is 12Z. Your moist layer extends up to about 800 millibars or so up into the atmosphere. Look at 18Z. That extends all the way up to just above 700 millibars. That is an extremely, extremely deep moist layer. Very favorable look for severe weather. That means your storms are going to be fed by a lot of juicy air in that low-level environment. And our shear profiles were already favorable for significant tornadic supercells. Very strong veering of those winds with height, even though, at first glance you might think, oh, the winds at the surface are a little bit veered out of the south-southwest. Doesn't matter. As we said, when your low-level jet is 50, 60 knots out of the south west, atop south-southwesterly 10 to 15 knot surface winds. That's going to create a lot of low-level veering and a lot of curvature in your low-level hodograph, and that's exactly what we got with this Little Rock sounding here. So an extremely favorable look for severe storms. Instability a little bit less here, about just under 1,000 joules per kilogram of mixed layer CAPE, but that is more than enough in this kind of kinematic profile for supercells. A little bit of wonkiness here in the mid-level hodograph. You see just a little bit of backing in these mid-level winds. Again, there's some debate on the what impact this has on the environment. If the backing is more noticeable, more so, greater than about 90 degrees of backing, then you may start to run into some issues. It can help to thwart the long track nature of mesocyclones. That can disrupt long track mesocyclones. But if you can generally establish a discrete storm mode, which we did in this case, and you have strong low-level shear for tornadoes, it's not going to matter a whole lot. And this is not that strong of backing. If we were to see something, like this in the hodograph, maybe that would be something to take note of. But this is very minimal backing, perhaps a result of the slightly displaced nature of the 700 millibar shortwave, a little bit off to the north, but still didn't really matter in this kind of profile. Strong low-level shear, decent instability. This was going with a discrete storm mode, was going to produce some significant severe weather. So very favorable look there at Little Rock at 18Z, 1 p.m. This was at Jackson, a little bit farther south. The cap was definitely a little bit stronger, farther to the south and southeast there. Held on a little bit longer. Jackson a little bit removed from our main area of storms there off to the north, but it was a decent area, decent sounding to look at just to the south of our area. This was at Shreveport at 18Z, much of the same as we saw at Little Rock. A little bit of capping remaining, but again, strong low level and deep layer shear was more than enough to sustain discrete tornadic supercells in this environment. 18Z Shreveport to 21Z Shreveport, much the same. A little bit of mixing there in the low levels farther to the south, 81 over 63. So that temperature dew point spread did increase a little bit, especially with southern extent, but still well within the range for tornadic supercells. A little bit of capping there remaining, but deep, deep moisture and a shear profile very favorable for supercells. Deep layer shear above 63 knots, effective bulk shear, effective storm relative velocity at or above 400 meters squared per second squared there. So very favorable look. This was the Little Rock 0Z sounding. You can see by then the winds had veered pretty significantly as the cold front approached. There in the low levels, very much southwesterly flow in the low levels now, but still out ahead of that into Mississippi. Here is Jackson at 0Z. Definitely a favorable look for severe weather with still very backed low level winds. And that would continue into the evening hours. This is 6Z at Jackson. No wonder the significant tornado threat existed well into the nighttime hours. A fully destabilized profile there, over 1,700 joules per kilogram of mixed layer CAPE. With this kind of profile, strong veering in the lowest levels there, over 300 meters squared per second squared of effective storm relative velocity, and a sustained discrete mode still well into the nighttime hours, favored the continuance of a strong tornado threat in the southern mode. All right, here's our visible satellite imagery. And as I was driving out from Norman, there was quite a bit of cloud cover and some showers across much of Arkansas. You can see some of these slightly agitated clouds in here. These were some showers in a broader swath of low-level cloud cover that was in place throughout the morning. And I thought, well, that may be a little bit of a negative as far as severe potential later on, but once I got to Little Rock, skies cleared up completely, and we got some very strong surface heating to take place there across central Arkansas ahead of this band of storms that was firing along this prefrontal trough there across southeast Oklahoma into western Arkansas, and these were again fairly discrete in nature, and they would move off into the central Arkansas vicinity and do their thing for quite a while, and it became pretty evident quickly that the storm in southwest Arkansas, initially near DeQueen, was going to be the one to wreak the most havoc across central Arkansas, at least initially. We're going to take a look at our infrared satellite imagery from March 31st. Infrared satellite imagery, I don't use it a ton on the channel, but it is a helpful tool to see how robust the updrafts are. Infrared satellite imagery shows the temperature of the clouds, and the colder the cloud tops, the more you see yellows, oranges, and reds, the more robust the updraft, the taller the storm. And it became apparent pretty quickly that southwest Arkansas storm was going to be the favored one for initially strong tornado potential. So you see the storms here, about 15 to 16 Z, start to fire along that prefrontal confluence band from northwest Arkansas into southeast Oklahoma. We continue on there, and you'll see these start to pulse up a little bit, but this one down in here, coming out of southeast Oklahoma, quickly began to show the coldest cloud tops and most sustained cold cloud tops here as it moved into central Arkansas. You'll see that point there, that little dark red point there, indicative of perhaps an overshooting top. Very cold, tall, robust updraft there. And this was the initial Little Rock supercell that produced the tornado in Little Rock. Supercell trailing behind it as well. And then we got additional activity back to the west that would show some strength. And this was the supercell, the second Little Rock supercell that would eventually be the long tracker that produced the Earl and Wynne, Arkansas tornado, as well as the Covington, Tennessee long track tornado there that moved north of Memphis. You can see the very dark red colors there in that supercell, indicative of an extremely robust updraft. No wonder that was one of the most prominent long track tornadic supercells of the day. Taking a look at the radar, you see some showers and thunderstorms off to the east of our target area. You do see some of those showers building. You actually do see, I believe, the prefrontal confluence band on radar there. It's that fine line of low reflectivity there in eastern Oklahoma down through north central Texas. I believe that is the confluence band. You'll see that storms do eventually fire back to the west of our showery activity out across Arkansas early. But you'll see those storms fire right along that confluence band there in southeast Oklahoma, northwest Arkansas, right around 15 Z or so, 10 a.m. Central Daylight Time. You do see quite a few updrafts along that line, but as we know, it does take some congealing in these strongly sheared environments of these updrafts to eventually allow them to become dominant, withstand the very strong shear. And that's what happened here. We got a couple of discrete updrafts along that prefrontal trough, and this would be our initial Little Rock supercell that produced the Little Rock tornado, and the one behind it that would eventually become the long tracker that produced the Wynne and Earl, Arkansas tornado, and then it marched into Tennessee, producing the tornado near Covington. Additional storms back to the west ahead of the cold front, still well ahead of the cold front, down here across northeast Texas into southwest Arkansas. This activity would remain discrete, and this storm here would be our long track supercell that moved near Tunica, Mississippi, and produced a few tornadoes there along its path. Storm stayed discrete, as we said, for quite a while, given the somewhat weaker forcing for ascent and the overall favorable parameters for a discrete storm mode. And eventually storms started to increase in coverage, and we got more of a line as we went into the nighttime hours here. This is at just after 5 Z, so 10 p.m. Central Daylight Time. Still some semi-discrete elements in there, but mostly a more messy mode as we went into the nighttime hours. Still a favorable environment out ahead of this for some embedded tornadoes that we saw overnight. All right, let's talk about some of the individual storms in the southern mode. This is some of my footage of the Little Rock tornado as it moved into the northeast side of the Little Rock Metro toward Jacksonville. It struggled to be condensed for quite a while. It was a very large wedge back in the hills on the west and southwest side of Little Rock, but it tried to condense a little bit as it came close to our location. Got some pretty close range footage of it as it crossed, I believe, Highway 167 there near Jacksonville. Pretty intense tornado, did some damage, and then moved off to the northeast and continued on for a little while after that. So let's look at the radar here. Started off, of course, as we said, as some showers and storms down in far northeast Texas, southeast Oklahoma. Those updrafts started to congeal, and it became pretty evident pretty quickly that this storm was going to be the first tornado producer of the day. It started to congeal, started to very quickly develop a low-level mesocyclone here, a little bit far from the radar at this point, but still it started to develop a mesocyclone, become a supercell, and the couplet strengthened as it moved off to the northeast. Very strong couplet there with a bounded weak echo region even, as it moved to the northeast of Dierks near Daisy, Arkansas, and would continue that low-level rotation fairly strongly toward Hot Springs. Had a little debris signature as it crossed near Hot Springs. You can see there in the correlation coefficient, coincident with that velocity couplet. So likely a brief tornado back in there as it crossed near Hot Springs and then approached Little Rock. Was definitely nervous sight watching the storm track right toward the Little Rock Metro. Given the environment it was in, and the fact that it was discrete, it looked like it could do some damage, make some chaos there in the Little Rock Metro, and unfortunately that's what it did. We were hoping it would wait until after the Little Rock Metro to produce a tornado, but you can see it's a little tough to tell because we're close to the radar, but you can see the small couplet there entering Little Rock, very tight couplet there. Definitely a little bit of a weird radar presentation because we're so close to the radar, but nonetheless a very strong supercell, strong tornado moving off. You can see it as it approaches, moves out of that cone of silence there near Jacksonville. A definite hook echo, strong velocity couplet with debris in the air there. So strong tornado for sure. And then it moved off to the northeast and quickly dissipated as the next storm, which would be the eventual Wynne and Earl, Arkansas tornado producer, and the eventual Covington, Tennessee long track tornado producer, was right behind it, probably cutting off its inflow. Let's look at some proximity soundings. This is going to be from Little Rock. And so we start off at 12Z, as we said. Deep moisture beneath that elevated mix layer, as we've seen throughout the entirety of this video so far for each target. But that capping quickly eroded by midday or so. This is at 18Z. That capping's still there, still not quite as unstable maybe as areas farther to the north up there in Iowa, where we had full clearing for a little bit longer, a little bit colder air aloft to destabilize the atmosphere. So maybe not quite as strong thermodynamically down to the south, but the low-level shear and the deep layer shear was definitely favorable for supercells. You can see how that hodograph progresses here by 18 and 19Z. This is at 18Z. Not much needs to be said about this. Deep layer shear over 60 knots, effective storm relative velocity almost 400 meters squared per second squared, strong veering of the low-level winds with height, and that is how you get these hodographs, 50 to 60 knots at a kilometer off the surface there. That's why you're seeing such large looped hodographs there, given that extremely strong low-level jet in place. Here's at 19Z. Much of the same there, despite maybe not quite as favorable thermodynamics, but if you have discrete supercells that are mature in this environment, once again, strong deep layer and low-level shear can overcome that and allow strongly tornadic supercells to persist in maybe slightly more hostile thermodynamic environments. So that profile remained in place for that secondary supercell that passed through Little Rock, and eventually the winds did veer in the low levels more out of the southwest, effectively ending the tornado threat for areas farther to the west. Let's move on to the second Little Rock supercell. This would eventually produce tornadoes, long track tornadoes that went through Wynne and Earl, Arkansas, as well as Covington, Tennessee. This was a shot of the tornado as it was going through Wynne, Arkansas. Great shot there. You can see that it's a very large, just looks like a big mesocyclone that's on the ground in its entirety. So a very strong tornado there. Somewhat rain-wrapped as well. We'll talk about that in a second as we look at our proximity soundings. This is the radar imagery from this storm. As we talked about, it started all the way back in southeast Oklahoma, moved off into southwest Arkansas. On the heels of that first Little Rock supercell, you can see it in the very top corner of the screen there. Here's our reflectivity screen. Here's the original Little Rock tornado. This was the supercells taking shape behind it that would become this supercell in question. Moved through Little Rock. Thankfully did not produce any tornadoes in the Little Rock metro area. We were on this storm as well, as it produced a very brief EF1 tornado west of Des Arc. I'm not 100% sure how you say that, but we were on this tornado, again, very rain-wrapped, but saw some minor building damage from it. Then it moved off to the east and started producing some significant tornadoes. This was near Wynne. You can see it has multiple couplets at times here. One back in here, one in here as well, so there could have been easily two circulations in progress at once. This went through the occlusion process quite nicely. Not a very deviant occlusion process here as well. You can see as it moves toward Earl, the ongoing circulation back in here near Parkin, new circulation taking shape off to the east and eventually takes over as it moves into Tennessee, crosses the river there. There's the old circulation crossing the river, new circulation developing out here out ahead of the ongoing tornado, and that would become the tornado that went through Covington right there, that very strong couplet. A very wrapped up supercell there, very textbook hook echo, debris ball at the end there, so very potent supercell there. Did go through the occlusion process, as we said. We'll take a look at why the it wasn't a sort of classic occlusion that you might see where the original circulation goes off well to the north into the forward flank while the new circulation moves off in the general direction that the storm is moving. Let's go ahead and dive into some of the proximity soundings. This is going to be from Memphis, Tennessee. So we'll start off 12Z wrap sounding at Memphis. Very weak low-level moisture to start off with beneath that inversion. That would change throughout the day as that warm sector shifted off to the east. This is about 20Z right in here. You see that we've destabilized somewhat. A little bit of capping inversion left, but as we've talked about, not too much of an issue when you have strong deep layer and low-level shear in place to sustain these discrete supercells. Strong wind profiles taking shape as well. Very strong curvature there in the low levels, veering of those low-level winds with height. Deep layer shear very favorable for supercells at 70 knots there. Effective storm relative velocity over 400 knots. So as you can see, just looking at from all the way from the northern mode to the southern mode, very widespread area of significant severe weather, significant severe weather parameter space. By 22Z, you see that the wind profiles just go pretty ridiculous there, over 660 meters squared per second squared of effective storm relative velocity as that low-level jet continues to strengthen. Those low-level winds are backed somewhat a little bit out of the south-southeast there. Very, very strong-looking photographs for significant tornadoes. No wonder this was able to produce several significant tornadoes along its life cycle. Continued into the nighttime hours before winds eventually did start to veer in the low levels. I want to take a look quickly at the soundings here. So first, I want to point out the deviant motion, or the lack of deviant motion. You can see that most of these tornadoes, especially in the southern mode, had very straight line paths. This is a Little Rock tornado. Of course, you're going to have a little wobbles here and there, but overall a very straight line path with these tornadoes. This is the Wynne, Arkansas tornado. Again, a few little wobbles in there, but no strong deviance like we might see, like we will talk about in the April 4th event. Very straight line pass. This is the Covington, Tennessee one as well. So you can see not a lot of deviance in these photographs or in these tornadoes, and you can see why from our photograph technique taken from the work done by Cameron Nixon and John Allen. We first look for our storm motion, which we'll use our bunkers right storm motion here. We then find the average of our winds in the lowest 500 meters of the atmosphere. So just by eyeballing it, probably be something right in there. And then we find the midpoint of those two, and that is our deviant tornado motion. So if we were to plot our storm motion vector, which is 230 at 48 knots, and we were to plot our deviant motion vector up to that point, you'd see they're not all that different. So we were not expecting a lot of deviant motion in the tornadoes on March 31st, and this is in part because faster storm motions tend to decrease tornado deviance. And you can see here 48 knots right mover storm motions. That's about 50 knots or so. That is pretty rapid moving storms, and so the deviance was not expected to be that high in any tornadoes on March 31st. And I also want to take a look at the photograph for why these may have been a little bit more high precipitation compared to the northern mode. I'm going to go to 22Z here. This is the 22Z Memphis wrap proximity sounding. So we've done this before where we can kind of take our photograph and produce an estimate of what the radar might look like for these storms. So here's our mesocyclone region of the storm. The precipitation gets vented out in the upper levels away, but you can see that it goes out somewhat ahead of the storm motion. Here's our storm motion vector. I'll draw that in blue here. So our storm motion vector, our tornado is going to be moving this way, and the precipitation is going to be vented somewhat out ahead of it, making visibility of these tornadoes a little bit on the iffy side. We can also look at our storm relative outflow above about 6 kilometers in the upper levels there. And again, anything above about 35, 40 knots tends to be a little bit more low precipitation. Anything weaker than that, closer to 20, 25 knots or so or less, tends to be more associated with high precipitation supercells. So if we draw our vector here to the photograph and from our storm motion vector, that's our storm relative outflow aloft. So this would be about 10, 20, about 25 knots or so. So we're verging more in that high precipitation supercell category. And that's exactly what we got here, looking at our images of these tornadoes. Even the Little Rock tornado, as you saw, was a little bit rain-wrapped. This one rain-wrapped as well. So these were a little bit more high precipitation in nature, at least initially, in this particular setup. All right, that's going to do it for our discussion of the March 31st event. Let's move on and talk about the April 4th event. Now, we're not going to talk about the April 4th event on its own. We're going to look at it more so as a comparison and contrast between it and the March 31st event, to show why the April 4th event was not quite as favorable for severe weather, despite very similar forecasts and background patterns for the April 4th event. You can see here, this is the day 13Z day 1 outlook on April 4th. Very similar look to it as the other one, as the March 31st event. 2 moderate risk areas, one up there in Illinois into Iowa, and one down to the south across Missouri into western Arkansas. This was a very well forecast event again, very synoptically evident. Day 3 had 2 separate enhanced risk areas, and by the 1730Z outlook on day 2, April 3rd, we had those 2 moderate risk areas in, and those pretty much stayed throughout the entirety of the event in some capacity. So very similar forecast to what the March 31st event had, but a very different outcome, as we said. Not nearly as many severe weather reports. Still a potent severe weather event, almost 500 severe weather reports in total, but you see just a few tornado reports sprinkled in there. Not your classic tornado outbreak, bimodal tornado outbreak that we saw on March 31st. Let's dive into the meteorology behind the April 4th event. We'll start out at 500 millibars, and this is at 12Z on April 4th, and the first thing you'll notice right off the bat, in as far as differences between March 31st and April 4th go, is the positioning and the progression of the trough and how different it was between the 2 events. And you'll see that here at 12Z on each day. So 12Z, April 4th, you see high amplitude feature, very strong trough, lots of strong flow rounding the base of that trough, lots of flow on the back side of the trough as well, signifying that the trough is still in its maturing phase. We want to see all of that flow rounding the base of that trough into the exit region. That tells us that the trough is definitely on the mature side. Not the case here early in the morning on April 4th. If we go back, though, notice the core of the position, the core of the trough is positioned somewhere in northeast Utah at 12Z on April 4th. We go back here to March 31st at 12Z, you'll see how far east the trough position is compared to April 4th. And you'll also see that flow, the strong flow, is all around the base of that trough into the exit region as it was about to take on that negative tilt on March 31st. So a much different orientation to the trough, even though both of these events feature very high amplitude, potent upper level features. And we go on, let's go forward here. You'll see as we go through into the afternoon, this is at 21Z, 4 p.m. Central Daylight Time, a much different progression to the trough. We still have a maturing trough, lots of flow, strong flow still on the backside of that trough. We don't really have a defined exit region, if you will. Of course, we know, we have the quote-unquote ski jump here, that strong flow leading into the exit region of the trough. But we don't have that trough really tightening up, taking on that negative tilt as we saw on March 31st. We go forward on March 31st, you'll see how tightly wound that trough is, takes on a much more negative tilt, much more compact exit regions or regions of interest, even though, as we said, the major threat for severe weather was over a very broad area on March 31st and on April 4th. But on March 31st, you had our well-defined exit region, strong defluence aloft, and a strong jet streak rounding the base into the exit region of that trough. Not the case on April 4th. You'll see that trough stays somewhat neutrally to slightly positively tilted, and we don't really have that tightly wound trough, tightly wound, well-defined exit region across the Midwest down to the Mid-South. We really just have this broad southwesterly flow with maybe a little bit of short waviness, if you will, going through that southwesterly flow, but it is much, much different from what we saw on March 31st. And we've talked about this before in this video, but positively tilted troughs don't mean that you're not going to see severe weather. Obviously, this trough produced some significant severe weather from the Midwest to the Mid-South. But you really want to see that tightly wound, negatively tilted trough with its defined features, defined exit region, defined jet streak rounding the base of that trough to really have your best shot at significant severe weather. This look on March 31st was definitely pretty textbook. This one, just not quite as textbook. And you can see how far to the west, how a little bit mistimed this trough was. The axis still back here, basically across the Rocky Mountains at this point at 4 p.m. Central Daylight Time on the 4th, whereas our axis here on March 31st was clearly into the eastern plains, verging into the Midwest and Mid-South, perfectly timed with our favorable low-level and surface features, low-level jet, warm sector, etc., for a significant severe weather event. This one, just not the case. So we continue on. It would start to take on more closed characteristics as we went through into the evening and nighttime hours, but still, even here at 5Z, 10 p.m. Central Daylight Time, still a positively tilted trough. Definitely a strong jet streak here in the exit region of this trough, but once again, not your classic look for severe weather as what we saw on March 31st. Let's go down to 700 millibars as well. You see the 700 millibar trough way out to the west as well. Not a really well-defined shortwave in here. Maybe you could argue one somewhere in here across Kansas there, maybe some slight curvature there in the height contours. We did see storms develop in far eastern Kansas, western Missouri, right around midday, lunchtime or so, moving off into eastern Missouri into Illinois eventually. That did become the main show for Illinois, but not as much of a well-defined shortwave as what we saw on the March 31st event. Clear shortwave there across eastern Nebraska into eastern Kansas, down into Oklahoma. Not the case for the April 4th event. As we go down to 850 millibars, you'll see a very similar look to what we had on March 31st. A broad area of low-level jet, 30, 40, 50 plus knots or so, across a broad region from the southern plains all the way into the mid-south and midwest. So low-level shear not expected to be much of an issue. Strong low-level jet in place as we saw on March 31st. Now at the surface, we had some significant differences between this event and the March 31st event. First of all, you'll notice the position of the surface low at 12Z on April 4th, somewhere in southeast Colorado right there. Watch where it is on March 31st. It's all the way up here in the Nebraska-Iowa border vicinity. So very significant positional differences in where the surface low is located among these two events. Now if we look and go through the progression of the surface low, you'll notice that it is much more sort of strung out, if you will, not quite as tight through much of the day across this region, just a very strung out, almost banana type low, as we colloquially call it in the storm chasing world. Kind of a banana low, strung out surface low, whereas on the March 31st event, we had a nice tight surface low up there in Iowa, with clearly defined frontal features and surface boundary features there draping off to the south. Not the case on the April 4th event, and that is all due to the orientation and progression of the upper level trough. As we've talked about before, what happens in the upper levels of the atmosphere is connected to what happens in the lower levels. So when you have a trough progression or ejection that looks like this, kind of strung out, a little bit more positively tilted, you're not going to have as favorable of a surface response as something like this on March 31st, where you have a nice ejection of the trough, takes on a negative tilt. You're going to have more, without getting too deep into the calculus and stuff, you're going to have more vorticity advection, more spin in the atmosphere, more favorable ingredients in that exit region of the trough that will relate to what happens at the surface, and you'll get a much more favorable surface pattern for significant severe weather as what we saw on the March 31st, in contrast to what we saw on April 4th. Still, we can denote some features here. Here's our surface low, southeast Colorado. This is at 12Z, warm front draped out to the east. You can see right through the pressure tongue there. You can tell by the wind shift. Winds out of the south of the boundary, winds more easterly to the north of the boundary. We'll fast forward here a few hours, go on into the late afternoon. Surface low, perhaps one center up in here into southwest Iowa. Tried to consolidate up there a little bit maybe, but still overall this strung out type feature. Warm front draped off to the east in southeast Iowa into northwest Illinois. That would become a big feature, a major player in the severe weather threat for Illinois during the early evening hours. Cold front draped out through this banana low back down to the south. A little tough to tell, maybe somewhere in here. It's hard to say for sure, but the cold front would spark some storms there in northeast Kansas into Missouri later on that would quickly become a line. And that was mainly our main surface features for this event. If we look now at our actual surface data, we'll see a few things happen. And this was also a critical difference between the March 31st event and the April 4th event, and that was vertical mixing. So we'll first take a look at our visible satellite. So this is our visible satellite from the morning of April 4th. You'll see quite a bit of low cloud cover across the region. Iowa socked in clouds, Illinois mostly socked in clouds there. The warm front somewhere in this vicinity lifting northward throughout the day as that surface low approached and strung out a little bit. We would get that moisture to surge northward and that warm front to lift as well. So you'll see the warm front, those clouds clear pretty quickly, but to the south of that we have almost 100% heating. We basically have full surface heating going on, and that initiated quite a bit of vertical mixing. Once again, we've talked about it before in this video and in many videos on this channel in the past. Vertical mixing, when you have that strong surface heating, you get warm air at the surface to rise, but that can also bring down drier air from aloft down to the surface, and you can see dew points dropped, and we had quite a bit, dew points drop in the afternoon, and we had quite a bit of dry air aloft to work with. We'll take a look at some soundings here in a second, but I want you to keep your eye on the green values here, the dew points, and these red values as well, the temperatures. So you'll see at 12Z on April 4th, we have 60s dew points down here into Missouri, southeast Kansas over into Illinois, that warm front surging northward. You can clearly see the wind shift, easterly winds to the north of the boundary, southerly winds south of the boundary. There's our warm front somewhere in there. So again, that warm front would lift northward, and by about 16Z, about 10, 11 a.m. or so, we had 60s dew points all the way up almost to the Iowa border, down into far southeast Nebraska. 79 over 64 at this station, 73 over 63, 80 over 63 here at Topeka. So rich moisture across the region. But watch what happens as the warm front surges northward. Keep an eye on those areas just south of the warm frontal zone. This is at 16Z or 17Z. This is 18Z. And for example, watch here at Kirksville, Missouri. So Kirksville, Missouri is right here. At this point, just perhaps just north of the warm front, still a temperature of 70 over 59. But by 18Z, the warm front had clearly passed, 81 over 65. So the moisture had increased at the surface, but the temperature was climbing. So at 18Z, 81 over 65 here at Kirksville. Watch what happens over the next hour. We crater to 86 over 61, so the surface temperature had increased quite a bit, and the dew point had dropped, and that is the direct result of vertical mixing. You can see that was rampant across the region. This particular station there, 86 over 65, 83 over 64 out here, 84 over 63, 84 over 60 there at that station. So vertical mixing was a huge issue, and we had some storms coming out of Missouri, but they were going into this environment that was extremely well mixed. And as a result, the tornado potential was a lot lower, more so outflow potential from these storms because the temperature dew point spreads were so high. Now, along the warm front was a little bit better. If we were to get any storms near the warm front, it was a little bit better. You'll see even in Iowa, despite this mixing across the region, 84 over 57 at this station right there, 84 over 61. Closer to the warm front, 77 over 63, little bit of moisture pooling there. 71 over 66, 84 over 65, so still very, mixing was very prevalent, but a little bit better temperature dew point spreads along that warm front, and that's why I thought it was going to really be needed for any storm to interact with that warm front to have any tornado potential at all, because the air was so well mixed elsewhere within the warm sector. So this mixing was a huge issue, even though we had quite a bit of low-level warm advection as that surface low moved northeast. Not quite as much, perhaps, as the March 31st event because of the strung-out banana nature of the surface low. We didn't have maybe quite as strong low-level warm moist advection to sustain that, to offset the vertical mixing from that pure sunshine. Also on the March 31st event, you'll recall we had some degree of clouds in the warm sector to at least help slightly temper the mixing. Here we had full-on sunshine, which was not going to be a very good prospect to keep those temperature dew point spreads down across the moderate risk area, especially within the northern mode. Down in the southern mode at the surface, we still had a broad warm sector in place, very similar to March 31st. 60s dew point stretching all the way from central Oklahoma, central Texas, all the way east into even Alabama and Tennessee. So a very broad swath, very broad warm sector for these storms to work with, but we just needed storms. That was the issue. There was really no forcing mechanism for storm initiation in the southern mode. If we look back at our trough positioning here, you'll see, especially with our southern extent, given the trough's a little bit more positively tilted, we just didn't have anything going on here to initiate storms other than that cold front up there in northeast Kansas that did fire off some storms in the late afternoon. But down here across Oklahoma into Texas, Arkansas, into Missouri, there wasn't really anything to initiate storms in this environment given the positioning of the trough, unlike the March 31st event where we had a nice prefrontal trough. Really none of that going on. No little short waves, no little prefrontal troughs to speak of. You'll see here not much going on at all at the surface. No real kinks in the flow. You even see some slight surface ridging there, if you will, across southern Arkansas. Not a favorable setup for storm initiation, even though the parameter space was getting to be fairly good. There just wasn't anything to set off storms in that southern mode, despite a very juicy air mass. Mixing not an issue down here, given closer proximity to your moisture source. Not much mixing going on down there. Temperature dew point spreads did get a little bit on the high side, 83 over 66, 80 over 66, 84 over 68 there across Arkansas. So there was perhaps some mixing ongoing, but still much less than areas farther north. We still had very juicy air mass down here into Arkansas, northeast Texas, northwest Louisiana, in that southern moderate risk area. Just no storms to act upon that juicy environment. All right, let's look at some soundings. Once again, we will look at some observed soundings first, and then we'll take a closer look at some of the individual storms in this event and look at some rapid proximity soundings for those. But for now, we'll look at some observed soundings. This is the 12Z Davenport, Iowa sounding. This is well north of the warm front. As you can see, very stout inversion there, 44-degree dew point at the surface, 46-degree surface temperature. So not super indicative of what the warm sector was holding. Still some elevated, most unstable CAPE, about 1,000 joules per kilogram, a little bit of elevated instability building. Here at Lincoln, Illinois, much of the same thing. Let's go down to the south a little bit. Here is Norman, Oklahoma at 12Z on April 4th. Moist layer at the surface, 68 over 68, so surface moisture looking very good, but that moist layer, very, very shallow, and that was a huge concern with this event, as was the dry air aloft. You can see all of this dry air, how much that red line, the temperature profile, and the green line, the dew point profile, are separated. That is a lot of dry air aloft, and I showed it in the forecast discussion video for this day on on water vapor satellite imagery, how much dry air there was in place. Not sure where it came from, but a huge plume of dry air was in place and advecting northeastward into the Midwest, and that is partly to blame for the mixing. You initiate vertical mixing in that pure sunshine across Missouri, Iowa, and Illinois, and you're going to bring this down to the surface. Even though dew points might start in the 60s, you're going to bring all this dry air down to the surface in that vertical mixing regime, and therefore dew points cratered a little bit as surface temperatures increased drastically. That's why we got those very high temperature dew point spreads. But nonetheless, here at Norman, shallow moisture beneath that strong area of dry air aloft, but our kinematics very, very good. Kinematics not an issue with this event, despite with the positioning of the trough aside and the forcing aside. This photograph looking very, very good. Veering of those low-level winds with height, indicative of strong warm advection, strong low-level shear, over 400 meters squared per second squared already in the warm sector by 12Z, amid strong deep layer shear for supercells. Here is Dallas-Fort Worth, much of the same, very shallow moist layer beneath lots of dry air aloft. We go to 12Z at Springfield, and you can see even more of that dry air aloft. Super deep layer of dry air aloft. And we talked about the effects of that dry air. Other than vertical mixing, you can have updrafts go up in this environment, and they're feeding off the air around it. And if you have dry air going into these updrafts, they may start to be less robust. They may get pinched off a little bit. You may see these anemic updrafts that struggle for quite a while until you can get some moistening in the profile. And so that was a concern as well with all of this dry air aloft and very shallow low-level moisture. Here at Springfield, though, at 12Z, lots of instability in place in the warm sector, over 2,200 mixed layer CAPE there with a very good-looking photograph for severe weather. Topeka, much of the same, removed from the warm sector there, but lots of dry air aloft you see as well. Here is 18Z at Davenport. Much of the same, not much had changed. See some of that drier air aloft above that inversion, still removed from the warm sector. Here is 20Z, 3 p.m. Central Daylight Time at Lincoln, Illinois. By this point, we were well within the warm sector at Lincoln, Illinois, 83 over 65. You can see that that temperature dew point spread getting much higher because of that mixing, that slight inverted V profile in the low levels. Not a super favorable sign for tornadic activity. Again, more that these drier low levels tend to favor more outflow production in storms as you get these rain-cooled downdrafts, and drier air from aloft getting sucked into these storms can evaporate the precipitation. You can get these rain-cooled downdrafts that can produce a lot of outflow and undercut any tornadic mesocyclones. But very unstable profile, 2,300 joules per kilogram of mixed layer CAPE there in west central Illinois. Deep layer shear more than adequate for supercells, 60 knots of effective bulk shear, strong low-level shear for supercells as well. 20Z at Topeka, you see the effects of the mixing there in spades. 87 over 60, very strong inverted V profile. So that was rampant across the entire warm sector. Down to the south, Springfield, unsure at this point if storms would fire that far south again on the dry line along in Oklahoma and Texas this early. The cap had eroded fairly decently. We still had a little bit of capping left, but you can also see some mixing down there happening as well. And storms, as we know, eventually did not fire in that regime, only in Arkansas overnight. 21Z Davenport, still north of the warm sector. Here is 0Z. We'll go to 0Z at Lincoln, Illinois. And you can see, even though the temperature dew point spread has come down a bit, still lots of dry air aloft, lots of capping in place. And we'll look closely at that supercell that went through near Lewistown, Illinois, produced a few tornadoes. It had a fairly short lifespan, did not produce long-track tornadoes as this capping grew in pretty significantly, and that helped to temper the overall long-track significant tornado threat. Photograph, also a little bit wonky. You see a little bit of wonkiness there in the low to mid-levels there, backing of those mid-level winds. This is a lot more prominent than what we saw on the March 31st event, where we saw, pretty solid photographs, a little bit of a kink aloft maybe, but still very favorable looking photographs. This one, very significant backing. This likely had some influence on low-level mesocyclone maintenance and perhaps strength, and perhaps limited the long-track tornado threat, as well as the dry air and capping in the low levels. We'll talk about that more here in a second as we look at some of the individual storms. Let's go to our satellite. Once again, we'll take a look at the satellite. So we'll go forward here. Once again, those clouds, as that warm front lifted northward, eroded fairly quickly. Fairly thick clouds south of the warm front, or north of the warm front. We started to see cumulus development there in southern Iowa by about 18 to 19Z. We had some storms actually fire in western Missouri there. You see this light coloring right here. That is a plume of cirrus, likely indicative of some slightly stronger forcing for ascent moving across the region. And these storms developed in western Missouri right underneath that cirrus plume. Not super strong cirrus, still got plenty of heating, as we know from our analysis of the surface data. So these storms didn't have any trouble firing. These cirrus didn't have a negative effect on storm initiation, as we've seen in some setups in the past. But these storms remained elevated for quite a while, given that strong capping in the low levels. They didn't do much. I believe these were tornado warned briefly, but these were mainly large hail producers and damaging wind producers, but still very robust storms. We got some additional development here to the west of those storms. This would eventually move into western Illinois and become our industry to Lewistown, Illinois tornadic supercell. Additional development as well back in southwest Iowa, closer to the surface low, at least that northern center of the surface low. Again, air very well mixed out in here. Was expecting those storms to remain mostly large hail producers as well as damaging wind producers. We did get a tornado out of them though, and we will go ahead and take a closer look at that storm that happened near Lacona and Pleasantville, Iowa, that produced a tornado. So we go into the afternoon, and you can see the overall coverage of storms much more sparse than it was on March 31st. Let's take a look at the radar here. So this is our radar imagery, our wide view. So we'll go through, and you see not much going on in the morning. Some elevated storms in northern Illinois that produced quite a bit of large hail, especially in the Chicago area. So those were well north of the warm front. No tornado threat with those. Those storms in Missouri started to fire up. They did take on some supercell characteristics early on. Then we had the regime closer to the surface low, the northern center of the surface low there in Iowa, and the storms back to the west of the initial Missouri storms fire up. We went through some interesting merger processes, and this became the show in Illinois, produced a few tornadoes near Industry and Lewistown, as well as some incredible structure. We'll talk about that a little bit more in a second. And then these storms in southwest Iowa produced a tornado or two down there near Lacona and Pleasantville. But overall, you'll see the overall coverage of storms for the April 4th event, not nearly as much as it was, or as widespread as it was on the March 31st event, because of that capping inversion that wreaked havoc on the environment for most of the day. And you'll see that Illinois stuff shrivels pretty darn quickly, and that's because of that cap building back in. and choking off those updrafts. And then eventually we did get some more forcing in play, and we got more of a line to form going into the nighttime hours. Down to the radar for the southern mode, you'll see through much of the day. This starts at 0Z. We had nothing going on through the entire day, except for some very elevated convection that formed in North Texas and southern Oklahoma, moved very quickly off to the northeast into Missouri. Didn't do anything at all. That cap ate it alive. Also of note, it was quite cloudy in the southern mode throughout much of the day. You see these greens and yellows here across Oklahoma into Texas into Arkansas. Those were some mid-level to high-level clouds that really were stubborn throughout the day and allowed surface temperatures to stay just a few degrees cooler than what forecast models were showing. The HRRR model was showing a little bit of activity there in north central Texas, perhaps a supercell developing out of that, but these clouds kept the temperatures down just enough to thwart any convective initiation down here through the day across Oklahoma, Texas, into Arkansas and northwest Louisiana. We started to see storm development about 1Z or so there in northeast Texas in the Arklatex vicinity. That was the first batch of storms that had forecasters' attention, but eventually the cap wreaked havoc on those. You see the line of storms there in Kansas along the cold front, damaging wind threat there, but those storms in Arkansas didn't do much at all. And then we had to wait until about 4 or 5Z to really get robust storm development here in western Arkansas to northern Arkansas, and that's when we saw some storms really start to take shape. That main forcing finally start to move in as that wave moved off to the east, and we saw some discrete supercells with tornado potential take shape, and this one here was a significant tornado producer near Glen Allen, Missouri, produced some significant damage there. Some tornado reports there in Arkansas as well. So these storms tried to get it done there overnight, but really they weren't able to do a whole lot besides that significant tornado there in southeast Missouri before they congealed into a line or more of a cluster, and the line moved in from the west. So not much happened in the southern mode because of the cap. We'll look a little bit into that with some wrap proximity soundings there in a second. All right, let's look at some of the individual storms in this event. The first one we'll look at is the Pleasantville, Iowa tornadic supercell. Produced a very photogenic tornado near Pleasantville, very tall tornado as well, very violent drill bit. I've seen some footage of it, and it was a pretty intense tornado at the surface. Very tall, though, very photogenic tornado there as well. Here is some radar imagery from this storm. You can see a bunch of storms here in southwest Iowa. Here is Des Moines. Here's I-35 right here. So these storms, you can see some pretty strong reflectivity cores in these. These were definitely hailers for quite a while, given somewhat weak low-level shear, which we'll take a look at in just a second. You can see also a three-body scatter spike develop as this southern storm takes a little bit of dominance away from the other storms. Strong reflectivity core, three-body scatter spike. We've talked about the three-body scatter spike before on the channel. That is when the radar beam gets sent out, hits the large hail in the storm, gets deflected downward toward the surface, and then gets deflected back up, hits the hailstones again, and gets deflected back outward, hence the three-body scatter spike name. So this is always usually indicative of two very large hail in this storm, and that is fairly accurate given the low-level shear was fairly weak at this time. And the temperature dew point spreads from the mixing were a little bit on the high side. So the tornado threat was low for quite a while, but as it moves off to the northeast, it starts to take more of a tornadic look. Couplet increases as it approaches the Lacona and Pleasantville areas there, and it produces the tornado southwest of Pleasantville. Wraps up pretty nicely, pretty textbook-looking tornadic supercell there. We'll shift our view here just a little bit. So you'll see here as it moves on, textbook hook echo there with that storm strong couplet, and it moves off to the north, somewhat deviant motion. We'll talk about that in just a second. Tries to wrap up once again just northeast of Pella, but still a very large hail threat as well with that storm, likely crossed the warm front, and the tornado threat was thankfully short-lived with this storm. Let's take a look at some proximity soundings. Now this is going to be near Ottumwa. You'll see it on the screen again there. You'll see it in relation to Pleasantville. It's going to be a little bit unrepresentative of the near storm environment, but it is close enough to where we can get somewhat of an idea. And I'll expand on that in a second. So throughout the morning, we're well north of the warm front at Ottumwa. You can see that inversion there, very strong capping. But quickly, we go from 19Z, where we're just north or on the warm front, 72 over 60 to 80 over 60. So clearly the warm front passes, at least on these RAP soundings, between 19 and 20 Z. You can see that the mixing had already commenced, very strong, very notable inverted V profile there, 80 over 60 at the surface, but our capping inversion had decreased somewhat, being a little bit closer to the forcing, a little bit better surface heating out there. A little bit closer to the surface low maybe helped to erode that cap fully. So we were uncapped by about 20 Z. Storm started to form in southwest Iowa around this time. And there, in the wind profiles, fairly strong deep layer shear for supercells. Not a ton of low-level curvature there. We do see some veering of those low-level winds with height. Effective storm relative helicity about 200 meters squared per second squared. So definitely a severe storm sounding, but again, the mixing was going to be very, very problematic in this environment. This is 22Z at Ottumwa. The RAP is showing quite a bit of convection here, so take this, especially the kinematic profile, with a grain of salt. But 86 over 57 here, that is a 29 degree temperature dew point spread at the surface. So mixing had taken its toll nearby this storm, but this storm was very close to the warm front. This is Ottumwa at 0Z, by the way. Still fairly well-mixed low-level environment. Strong instability, 2,500 joules per kilogram of mixed layer CAPE. Our wind profiles had improved somewhat, though. Some stronger veering in those low-level winds with height, strengthening of those winds as well, and a nicely curved hodograph, about 300 meters squared per second squared, of effective storm relative helicity. So our environment was pretty darn good for storms, and this was as the storm was ongoing. So the thermodynamics, very strong there, very strong instability, strong low level and deep layer shear, definitely favorable for supercells. Now, tornadic supercells were a question, though. If we could get somewhere where these spreads were a little bit less drastic, then we would see some much better chances for tornadogenesis in these storms. And that's what we got near the warm front. You can see, so Pleasantville is kind of right in this vicinity, right in there. You see that away from that, Ottumwa 79 over 61 at 0Z here, 7 p.m. Central Daylight Time, but closer to Des Moines, 66 over 59. So we're right in that sweet spot, right on the warm front. You see the warm front, the wind shift is right in this vicinity. There, I believe this storm interacted with the warm front, where spreads were a little bit lower, low-level shear was a little bit stronger, and that is why this storm produced a photogenic tornado. Thankfully, it likely crossed the warm front pretty quickly. We started to get some capping to build back in, and the tornado threat was short-lived with that storm, thankfully, in that kind of environment. All right, let's turn our attention to the Illinois storm. There was a tornadic supercell that moved through western Illinois near Lewistown. This was a very photogenic supercell here that produced a couple of tornadoes near Table Grove and then another one near Lewistown that you see here. Very nice condensed tornado. Thankfully, the significant tornado threat was not long-lived out of this supercell as well. We can owe that to the cap, which we'll talk about in just a second. So here's some radar imagery from the Lewistown storm. Interesting early progression with this storm. Lots of updrafts in close proximity to one another. Just a big blob out here coming out of northeast Missouri. But we eventually got some mergers to occur, and you'll see here that we start to get one main supercell there as it approaches Macomb. Interesting evolution, though. It's almost as if this, acting as the hook, is a supercell on its own there. It has its own hail spike. You see the three-body scatter spike here emanating from that hook portion of this storm. As it's starting to wrap up, you see the shear signature starting to increase with that storm. But eventually, it takes on a much more classic supercell look. Interesting there, you have almost two hail spikes from the storms, one here from this core and one here from that southern core. Very interesting evolution with this storm. Definitely an HP monster, high precipitation monster here. Does start to produce tornadoes at this point south of Macomb as it moves off to the northeast. Then takes on a little bit more of a classic supercell shape as it approaches Lewistown. That hook clears out a little bit, and we get a little bit more of a classic hook shape there with that supercell. Here's a little bit of a closer look, a little bit more of a zoomed in look on this storm. Again, very interesting evolution there as it's producing tornadoes near Lewistown. You'll see that the Lewistown tornado, Lewistown sits right here. Tornado is right here. Watch the path that the Lewistown tornado takes. Definitely moves off to the north a little bit more. Quite deviant motion. We'll go over that in just a second. And I do know there was one chaser that was caught in this tornado. I'm not sure if it was because of deviant motion or not, but always have to be aware of deviant tornado motion with these supercells. So we'll take a look at the Peoria, Illinois sounding. We're at proximity soundings. You'll see it on the map there. Fairly close proximity to Lewistown. So we start off once again very similar to the Ottumwa sounding north of the warm front. Strong inversion there. We do see some mixing as we go into the mid-afternoon hours, 82 over 65 here. Quite a bit of dry air aloft. That cap does erode somewhat though. As we go into the afternoon hours, we do see it still evidence of that cap as we go into mid-afternoon. It doesn't fully ever erode, but we were able to get some supercells to fire and eventually converge into one supercell here going into Illinois. But watch what happens with the cap as we go into the evening hours. This is at 0Z, 7 p.m. That cap really, really builds in. Shallow, moist layer there despite surface moisture and surface temperature dew point spreads improving 77 over 64. But that cap is very, very strong. And as we said multiple times, if you have a mature supercell, tornadic supercell ongoing, it can last into an environment like this. But this cap is extremely, extremely strong. And that was what was able to choke off this storm as it moved toward Peoria. If we bring up the radar again, you'll see as it moves toward Peoria, it starts to lose it. This second cycle here after the Lewistown tornado tries to cycle again, but can't quite do it. Looks very outflowy. Takes on that dog leg type shape with the hook echo. Shrinks in size. You can see the supercell shrinking in size there. Just getting absolutely choked off by the cap. Loses its structure there. And as it passes through Peoria, not much of a severe weather threat after that as it shriveled up pretty darn quickly. That is because of the cap. Sometimes the cap is just too hostile and builds back in too quickly, and we never fully eroded it here. So back a few hours, back mid-afternoon or so, that cap was definitely manageable. Only about minus 38 mixed layer convective inhibition there. That is doable. If we can get some surface boundaries, that warm frontal zone provides a little bit of extra oomph along it. And the storms, as they interacted with it, were able to produce tornadoes. But once those storms moved farther into Illinois, that cap grew a little bit. They eventually did probably cross the warm front as well. Those storms were just no match for this cap. Very strong capping inversion there, building back in. That started to choke the storm off and allow it to shrivel. Also, that capping inversion was clearly evident with the storm structure. Not often you see pretty ridiculous storm structure like this with a tornado. This is a great shot showing the pancake stack type structure there with the incipient tornado near Lewistown. And this is a classic sign of a storm that is struggling with some convective inhibition. This combination comes from strong streamwise vorticity with a little bit of convective inhibition in play. So let's take a look at our sounding here. We'll go to our 23Z sounding. First of all, once again, you see that cap building back in that low to mid-level portion of the atmosphere there. You also see some streamwise vorticity here in the low levels, that lowest couple kilometers or so. Once again, that streamwise vorticity, our storm relative wind vector, and our horizontal vorticity vector there perpendicular to the hodograph. Lots of that in the lowest levels of the hodograph there through that lowest couple of kilometers. So that coupled with that streamwise vorticity coupled with that capping inversion always yields some pretty impressive structure, and we were able to have just enough forcing to allow the mesocyclone to drill through that capping inversion. But that structure and tornado combo, that is always a sign of some sort of capping inversion in play with strong streamwise vorticity. All right, let's talk about tornado deviance. We already looked at the Lewistown tornado and saw how deviant it was. Definitely had a northward motion as it dissipated. This was the Lewistown tornado track. You can see a very deviant path, if you will, with quite a bit of northward motion, especially toward the end of the path. And it's easy to get caught off guard by this, but we can actually forecast deviant tornado motion. We'll use our 23Z Peoria, Illinois wrap proximity sounding just as an example, and we'll use the same technique we used for the March 31st case, that technique used in Nixon and Allen 2021. We'll first plot our storm motion. We'll use our bunkers right. Then we'll plot our average winds in the lowest 500 meters of the atmosphere, roughly about right in there. And then we will find the midpoint of those two. So if we were to draw our storm motion vector, 225 degrees at 37 knots, and then our deviant tornado motion vector, unlike the March 31st case, you will see a decent amount of separation between these two. In other words, tornadoes were expected to be somewhat deviant on this day. So
if you're forecasting or you're going out to chase tornadoes, always make this a part of your forecasting process. It's this very simple deviant tornado motion technique that can tell you, whether or not you should be north of the tornado. And the reason that deviance was a little bit higher in the April 4th case was perhaps because of slower storm motions. As we said for the March 31st case, faster storm motions tend to decrease tornado deviance, whereas a little bit slower storm motions here, 37 knots for the April 4th case, and this sounding compared to about 50 knots or so for the March 31st case. Slower storm motions can increase tornado deviance a little bit, as you can see by our technique here, a little bit more deviance in these tornadoes, and that's exactly what we saw in both the radar imagery and the eventual damage survey of the Lewistown tornado, and for that matter, the Pleasantville, Iowa tornado as well. Just one last note here on the southern setup. I pulled a few RAP soundings from Russellville, Arkansas, right in the middle of the moderate risk down there to show you that the soundings were similar to what we saw up north, maybe a little bit less mixing, a little bit better temperature dew point spreads down here, but that capping inversion held on. This is at 12Z. You see pretty significant capping there at Russellville. This is at 18Z, 0Z, and then 6Z. So you see throughout the day that capping inversion really hangs on. And that is okay that was okay up to the north when you had some you were in closer proximity to the main forcing, closer to that surface low, closer to the surface boundaries, the warm frontal zone, for example. And so you had some forcing mechanisms that could break this cap. Well, down to the south, that forcing was nebulous given the trough was lagging off so far back to the east. We'll go through this once again, the 500 millibar map. You'll see the forcing is just way back to the west. The main trough is way back out here to the west compared to our moderate risk zone over here, that the forcing didn't really arrive until late that night, enough to break the cap, finally initiate some discrete supercells here in southeast Missouri, northern Arkansas, and that's when we finally got that cap to erode enough to get storms to develop. This is an 8Z RAP sounding from Cape Girardeau in proximity to the Glen Allen, Missouri significant tornadic supercell. You see that cap did erode up there to the north a little bit, so we were able to get efficient supercell development, strong low-level shear, strong deep layer shear, definitely an environment favorable for significant tornadoes up there. But even though these soundings are similar, definitely the entire area, the entire event struggled with a capping inversion. But if you have some forcing mechanisms like frontal boundaries, short waves, etc., you can break this cap, and this is not that much of an issue. But when you don't, when the forcing is nebulous or non-existent, this is going to stay put, and you're not going to get storms to fire, and that's why we didn't see anything fire down in the southern mode until very, very late, at which point it did produce significant tornadoes given this environment, which ended up being fairly favorable for a strong tornado threat. So that's going to wrap things up for this video. This was definitely a long video, so if you enjoyed it, if you made it to the end, let me know in the comments below. But this was just a very interesting juxtaposition between these two setups, with a lot to cover among the two setups, and it just goes to show all it takes is a few small tweaks here and there in the orientation of the upper level trough, the strength of the cap, the strength of the surface low, the orientation of surface boundaries, etc., to take an event from one where we see just a few tornado reports, such as April 4th, to one where we see one of the more prolific tornado outbreaks of all time, such as what we saw on March 31st. So very interesting event, a lot to cover, and interesting to see how two very similar background patterns created two very different outcomes among these two setups. So with that, thanks for watching, and we'll see you in the next video.